Welcome everyone to Astronomy on Tap for November. I'm Dr. Cameron Hummels. I'm a computational astrophysicist at Caltech, and I will be one of your MCs for the evening. Our other MC is Dr. Kaylin Henderson. There's Kaylin.
Hi, everybody. Good to see you again.
Kaylin is an astronomer at IPAC, which is a NASA center on Caltech's campus. So yeah, I hope you guys are having a good evening as we lead up to American Thanksgiving. If you're in Europe, maybe you're not going to celebrate this week. And I guess if you're in Canada, you already had Thanksgiving, I think, like a month ago. I'm not clear on all the dates of the various Thanksgivings, but
because in Canada, I know the toilets flush backwards or something, right? No. So maybe it's all mixed up.
Yeah, we've got a great event tonight. So Casey and Kishaloy are our speakers for this evening. Do you guys want to turn on your cameras and your microphones? Welcome, guys.
Hello.
Yeah, so if this is your first time coming, we have these events once a month, Astronomy on Tap. We did not start them. They were actually founded in New Haven and then in New York City like 4 or 5 years ago. And there's a lot of different chapters around the world that have these in person at local pubs. And obviously not many of them are actually happening in local pubs right now because of the COVID pandemic, but that's good news for you as a stay-home audience, because there are probably like 10 or 15 chapters that are still going throughout the pandemic, and they're all on YouTube or on Facebook Live or various streaming services. So if you go to astronomyontap.org, it has a list of all the events that are going on throughout the month. We're the only ones this week, I think, because the holidays and such. But you can see it. I've also included the link in the description, so you can go to that link and check it out and see the other events that are going on and watch those or watch the recordings. But there's lots of really good speakers at various different departments that are hosting these. And hopefully, if this vaccine comes along, pretty soon we'll go back to having in-person events, and we'll continue to do those here in Pasadena and in Los Angeles. Two other quick announcements. So our sister series, Astronomy on Tap in West LA, had their first event last week. Of course, again, this was online, but it will be in Westwood. It's being hosted by our colleagues at UCLA. So it'll be in Westwood and Brentwood area when things go back to normal. For those of you who are in the western part of Los Angeles, there may be something closer than coming all the way out to Pasadena. And I was just made aware of some colleagues who've started well, it's not so much Astronomy on Tap, but it's public astronomy lectures and activities that are going to be entirely in Spanish. And we have the link below in the description to their YouTube page. They just created it this week. So there should be an event coming up in the next month or so that's entirely in Spanish for our Spanish speaking colleagues.
Oh, that's cool. Is that based in LA or is it based somewhere else?
I was contacted by Nico, who's a PhD student at University of Arizona. But it's going to be between various different collaborators, I think worldwide, and that'll like be a central YouTube hub where various people can contribute and give talks and that sort of thing. So I think there will be a number of us involved. Of course, I don't speak Spanish, but I can grab people who speak Spanish and try and get all the right people together to be able to do this. And the last thing to announce is we have a sister series that's a public lecture, a stargazing lecture that happens once a month. Our last one, which was 2 weeks ago, was done by Katie Bauman on observing the first black hole with the radio telescopes and as part of the Event Horizon telescope. And our next one will be on December 14th. So that is a Friday, 2 weeks from this Friday, given by a professor at Caltech named Vikram Ravi, who's also doing radio stuff, but less about black hole detection. And I think he's going to mostly be talking either about fast radio bursts or black holes. I'm not sure which, but
I think, do you mean the 18th? The 18th is a Friday.
Oh, is that what I mean? That
yeah,
may be.
Yeah.
Is the 18th a Friday?
Yeah,
Okay,
yeah.
then that's when we're doing it, not on the 14th.
Okay. Just wanted to
I
make
hope
sure.
that's not too late for people. But there will be announcements on our website and on social media and on our YouTube page if you want to check that out. So, what are you guys drinking? Since this is Astronomy on Tap.
Ooh, I'm drinking, oh, you can't tell with my background, the finest Corellian wine this side of the galaxy has to offer.
I think I think Star Wars is fiction, unfortunately. What?
No. I feel like you haven't watched this show before. They're documentaries of a series of space combats that took place in the past and very far away.
I see. Okay.
Casey, what are you drinking?
Actually, just water because it is 10:30 p.m.
That's fair. Yeah, Casey's joining us from Baltimore or from Maryland?
From Maryland, yeah.
Okay.
Near Washington, D.C.
Near DC. Okay. And Kishaloi, what are you imbibing?
Bourbon.
Ooh.
Oh, bourbon. Good choice. Good choice. I actually have to run to my refrigerator and get something. I forgot to get something in the prep for this, but I'll report back. Okay. Well, do you guys have anything to say before we launch into talks? Any other small talk or short talk, as I said, Bert?
Yeah, short talk. Just thank you, Casey, for joining us from the East Coast.
Yeah.
No, it's a lot later there, probably a lot darker too, but we're very happy to have you. We're very excited for the talk.
Awesome.
Oh yeah, and I guess. Oh, I'm sorry. I didn't mean to speak over you, Casey.
Oh, no, I was just saying thanks for having me.
Yeah. And I forgot to mention our layout for tonight. So each of our speakers, Casey will start us off with about a 15-minute presentation. We'll take Q&A for her. Then we'll switch over. Kishaloi will give a roughly 15-minute talk, have Q&A for that. And then we'll have roughly an hour's worth of pub trivia. It's super interactive. We have a new interactive computer program so you can click in answers and then it pops up on our screen and on the slides and such, so everyone can see what everyone else is responding.
Yeah, we think it's going to go a lot better than those of you who joined us for the past couple. We had some technical difficulties.
Yeah.
So we think it's going to be way better.
It's going to be super awesome.
It's going to be super awesome. Also, for those very astute program watchers, you'll note that we now have reached a super majority of Astro on Tap coordinators who have the initials CH. We are at 75% tonight. It's a very special night.
Sorry, keep it up.
And KD is also very exciting too.
KD is very good. KD is very good. Okay, cool. So do you guys, except for Casey, do you guys want to hide your screens? And I will introduce our speaker, Casey Honeyball. Dr. Casey Honeyball is a postdoctoral fellow at NASA Goddard Space Flight Center. She has extensive experience in observing, instrumentation, and telescope operation, and is currently conducting a large-scale survey of the mid-IR hydration properties of the lunar surface using the NASA Infrared Telescope Facility, the NASA DLR Stratospheric Observatory for Infrared Astronomy, also known as SOFIA. In her free time, she enjoys working with horses, self-teaching herself piano, and is currently undergoing a whole kitchen renovation. That is pretty intense. I'm sure, on top of, and you probably read about Casey or read some of her results in the last 3 weeks or so. It was all over the news with a big press conference about the very topic she's going to be talking about tonight, and that is the detection of water on the sunlit side of the moon for the first time. So it's super, super exciting. And Casey and I go back a ways. She was actually an undergrad when I was a postdoc at Arizona, and now I'm still a postdoc, and now she's a postdoc too. So time flies and I don't. So I welcome Casey. Thank you very much for joining us, and take it away.
Great. Thanks so much for having me. All right, let's get this sharing. How does that look?
That looks perfect.
All right, great. So thanks for having me. As you said, I'm going to be talking about water on the sunlit surface of the moon using the Stratospheric Observatory for Infrared Astronomy, SOFIA. But first, I'm going to start with some background. So for many decades, the moon was thought to be dry, but beginning in 2008, evidence for lunar hydration began to emerge. Sol et al. 2008 measured high hydrogen contents in pyroclastic glasses returned by Apollo samples. And pyroclastic is basically just a volcanic feature. So when a volcano erupts on the surface of the Earth, it erupts these volcanic glasses that are just like glass beads that are deposited onto the surface. And so during Apollo, we collected some of these kinds of samples, and we were able to see that there was hydrogen in these, which led to the discovery that the moon isn't completely dry. Then in the following year, in 2009, 3 spacecraft reported an absorption feature at 3 microns, which is attributed to hydroxyl, which is OH, or possibly molecular water, H2O. And so these studies were the first to reveal that some sort of hydration is present on the lunar surface. So while these observations were showing that the moon is not completely dry like we had originally thought, the observations have not been able to distinguish between hydroxyl, OH, and molecular water, H2O. And that is because of the ambiguity in the 3 micron band and lack of laboratory studies. So the 3 micron band is created by the symmetric and asymmetric stretch of the OH bond. And both hydroxyl and molecular water exhibit this 3 micron band. This plot here is showing different forms of water on this water and hydroxyl at different forms at 3 microns. And you can see that they're very similar in spectral shape. So further complicating the 3 micron band is that hydroxyl attached to different metal cations can mimic molecular water. And currently the band shape, center, and strength of it center and strength cannot be predicted for hydroxyl attached to different metal cations. And so we cannot separate hydroxyl from molecular water at 3 microns. In the UV, water ice band has been used to detect ice deposits at permanently shadowed regions at the lunar poles, but it has also been detected on the sunlit surface of the moon. And it is unknown what is causing the water ice band ratio to vary diurnally on the sunlit surface of the moon. And Hendricks et al. 2019 is assuming that if adsorbed water behaves similarly to water ice in the UV. But there's no lab data to confirm this, and so hydroxyl cannot be ruled out as being the cause of this UV water ice band ratio on the sunlit surface of the moon. So therefore, there's been no definitive evidence of molecular water on the sunlit surface of the moon. So in order to prove the presence of molecular water on the moon, we needed new methods for its detection. And fortunately, molecular water has a third fundamental vibration, which occurs at 6 microns, that is explicitly due to water without contamination from hydroxyl. This 6 micron band is strong and narrow and well suited for detecting lunar water. Now, this method is new to remote sensing, but it is not new to the detection of water in geologic thin section samples and has been used since 1962 to measure the abundance of water. It has even been pointed out in literature that 6 micron observations of the moon could prove the existence of water. So the 6 micron band, while new to lunar science, has been observed in remote sensing measurements of samples in planetary bodies. Apollo samples measured at ReLab and meteorite samples measured at APL exhibit a 3 and 6 micron band shown in plots A and B. And from spacecraft, a 6 micron band has also been observed on Mars, as shown in the plot in C, and in asteroids, shown in D. The 6 micron feature has even been mapped on Mars. So these are examples that show if water is present on the surface of the moon, it should exhibit a 6 micron band. Now, currently, however, there are no spacecraft capable of making 6 micron observations of the moon, and ground-based telescopes, the atmosphere of the Earth is completely opaque, and so ground-based telescopes can't make 6 micron observations. This plot here shows the transmission of the atmosphere from Mauna Kea Observatory in blue, and at 6 microns, there's just no signal available to measure. However, the higher the observatory, the more the atmosphere opens up. And this allows us to use the Stratospheric Observatory for Infrared Astronomy, SOFIA, to look at the moon at 6 microns. And SOFIA flies at an altitude of about 14 kilometers, which is actually above 99.9% of the atmospheric water vapor, opening up the 5 to 8 micron region allowing us to make observations of 6 microns on the moon. And the SOFIA transmission is shown in the green. So with SOFIA, we have made the first observations of the moon at 6 microns in search for molecular water. So on August 30th, 2018, we had our first flight on SOFIA. We observed 2 different locations, a Mare reference at low latitudes and the Clavius crater at high southern latitudes. The image of the moon shows the location of each slit where we acquired data along, and also a photo of me on SOFIA observing the moon. So what we found is that from these observations is a prominent 6 micron emission feature. And this plot is showing the strongest 6 micron band that we observed in the Clavius crater region at high southern latitude. The image of the moon is of the Clavius crater, showing the slit image overlaid where the blue represents the abundance of water. So the band we detect is about 2% in strength, and we attribute it to the water molecule. And this is the first unambiguous detection of water on the sunlit surface of the moon. So just to be sure that this is actually due to molecular water, we compared the lunar 6 micron band properties to literature values of the fundamental HOH bend, which creates the 6 micron band, from Falk 1984 and other observations. The lunar 6 micron band centers that we observe all fall within the cited band centers of the HOH bend, and the distribution of the band centers is shown in the histogram on the top plot, with the moon, meteorites, and water-bearing glasses 6 micron band centers overlaid. If we take a look at the bottom plot, the moon and meteorite 6 micron bands are very similar in shape, center, and width, and we find that the lunar 6 micron band is broader than water-bearing glasses, with the band center shifted to lower wavelengths. These observations are different because they are likely because they have different chemical compositions. And so with these results, we are confident that the 6 micron band that we observe on the moon is actually due to molecular water. So next we wanted to estimate the abundance of water present. And so to do this, we use the strength of the 6 micron band, which correlates to the absolute water content and is commonly used to measure water in thin sections. So we are using the strength of the band to estimate the abundance in remote sensing data, which has not been done before. So to do this, we use water-bearing glasses with known abundances of water that feature both a 3 and 6 micron band. And we derived an empirical relationship between the depth of the 6 micron band and the abundance of water present in the glasses. The spectra that we used are shown in the top and middle plot, and the empirical relationship that we use is shown on the bottom. So we estimate that there's an abundance of about 100 to 400 parts per million of water in the Clavius crater region at high southern latitudes. The histogram shows the abundance of water for each spectrum in the Clavius region. The plot, this plot on the other side is showing the abundance of water with latitude. And we also compared that to MCube, the moon mineralogy mapper data, which shows the abundance of total water, which is hydroxyl plus molecular water derived from the 3 micron band. So SOFIA is in black and MCube is in red. And what we see is that with SOFIA, there is an increase in water abundance at low latitudes, whereas MCube increases in total water abundances with higher latitudes. And this is kind of opposite of what we expected. We expected the SOFIA data to show an increase in water with increasing latitudes, but instead we're seeing the opposite. And we think this is likely due to the observations with SOFIA being across Tycho crater ejecta. So we expect that this is not a global phenomenon and more likely a localized phenomenon. But all the abundances that we do measure with the 6 micron water band all fall within the error bars of the MCube total water abundance. So one thing we wanted to do was simply understand where the water could be stored on the lunar surface. And there are a few places that it can be. And 2 possible locations are chemisorbed on the surface of grains or sequestered inside impact glasses. At the latitude and temperature of our 6 micron observations of the moon, models suggest that only 3 parts per million of water is available for chemisorption on grains. Now, this is a lot lower than what we actually measured with 100 to 400 parts per million. And so this implies that all the water that we're observing is likely stored within impact glasses and giving abundances. If you constrain all the water to these impact glasses, that gives us abundances of 300 to 1300 ppm of water. And these results are consistent with water being produced from pre-existing hydroxyl during a micrometeorite impact. So our next step is to simply observe more, a lot more. Currently, we have been awarded an additional 2 hours of observing time on SOFIA, and we are anticipating the observations being scheduled in the spring of 2021. But we have also applied for an additional 72 hours of observing time on SOFIA to look at the moon over the to look at the moon in more detail and map water across the surface of the moon. So with these more observations, we will be able to characterize lunar water and work towards understanding the lunar water cycle. We want to understand the source and how it moves across the surface and if it does at all. And we want to understand locations where water might be concentrated and extend SOFIA data to look for and identify possible rare minerals, such as olivine, that could be concentrating water. So when we finally get the chance to observe on SOFIA, we will make maps of the moon at different lunar phases to understand how water moves across the surface of the moon, which can tell us about the source and retention of water. But we also want to make maps of the polar cold traps to support NASA's Viper mission, and maps of volcanic features like the pyroclastic deposits I described at the beginning, and silicic domes, and also crater central peaks that could concentrate water and may have rare minerals. So there's currently still a lot of work to be done, and the observations that reported these first detection are just the beginning. Thank you.
Hooray! That was great. Thanks, Casey.
Thank you.
There are lots of good questions. I also have questions just to make sure I understand everything that you just laid down for us. So, okay, first I'm gonna switch back to there we go. Okay, so one, is there really a person's name who's Sunshine who works on Sunshine on the Moon? So
yes.
At all 2009. That's awesome.
Jessica Sunshine. She actually predicted that the water was varying or that water was responsible for variations in the 3-micron band, but couldn't prove it at the time.
Okay, that's awesome. Okay.
Does that mean, is she a Dr. Sunshine?
Yep.
That's so cool.
Okay, so just to make sure I get this straight. So there were previous observations of the moon in the infrared at the 3-micron band that indicated that there was something there, and it was either water, H2O, or hydroxyl, OH, right? But you couldn't tell them apart. And then you used SOFIA, which is the telescope that sits on a 747 and flies up above most of the atmosphere. So it doesn't have the absorption problems of our own atmosphere getting in the way. And you looked at 6 microns, which is another water feature that doesn't have contributions from hydroxyl, right?
Yep, that's exactly correct.
Okay, and you looked at these 2 sections of the moon. One was the Clavius crater that was like at 70 latitude, like nearer the pole, but not at the pole.
Right.
And then something that was in the basalt basins. What was that? What feature was that? Did it have a name or?
I just call it Mare reference. It's in Mare Tranquillitatis.
Oh, okay. So, that's cool. The Sea of Tranquility.
Yeah.
Bringing it all back to the Apollo mission. Okay, cool. So then you were looking at those, and then you showed that there was the 6-micron signal. But interestingly enough, there was more of it at low latitude, closer to the equator, than there was at higher latitude. So there was more water closer to the equatorial region than closer to the polar region from those samples.
So we actually find that at the equatorial region and the Mare reference, there's no water. But we see that at high southern latitudes, there is a lot of water. The plot that I showed with latitude is only covering like 55 to 75 degrees in latitude.
From the Clavius.
Right.
Okay.
Right.
Okay. That's interesting. So the Maria region, which is all just like volcanic black salt, is dry as a bone.
As far as we can tell, yes. We need further observations to really confirm this, but yes, at the moment, we think that at least that spot is quite dry.
Okay. Okay. And with Clavius, that's like a crater site, or it's the highlands as well, or it's a mix of both?
Yeah, so Clavius is located in the highlands, but Clavius crater is one of the largest craters visible from Earth with your naked eye on the moon.
Okay. 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 And then you were saying that the water, it's not like puddles of water. First of all, it's super, super low. You said it was like 100 parts per million or 400 parts per million or something like that. But that is, you said it was mostly tied, it was found in, or it's based on the models, it's mostly in the glasses because there isn't that much that's just like stuck on the grains or absorbed in the stuff, in the
Yeah. Yeah, so based on so if you were standing on the moon at the time of our observations, it would have been 2:30 in the afternoon, so it would have been kind of warm. I think our observations had a temperature of 320 Kelvin, so it was kind of warm, and it was kind of noon-ish time on the moon. And so when we did models, it showed that if any water was going to be there on the surface of the grains, it was a very, very low amount. And so the fact that we were able to see water present compared to what the models predicted meant that something was sheltering the water and protecting it from being lost and, to the harsh lunar environment. And so that made us conclude that the water's being sheltered. And so we think it's being stored within inside these impact glasses.
Okay. Okay. So you think it's there, but you haven't directly detected that it's present in the glasses, but where else could it be? Because it would have just evaporated or sublimated away.
Right. Exactly.
Okay. That's crazy though. It seems strange that because those glasses, aren't the glasses formed during like a micrometeorite or during a meteorite impact? And so
Yeah.
the high temperatures associated with that would also evaporate that water too, right?
So it's interesting. So actually those high temperatures are possibly what's creating the water from pre-existing hydroxyl. So if you have two hydroxyl molecules sitting on the surface of the moon that were formed from solar wind interactions with the surface, then you can take these two hydroxyls and combine them to make water. But in order to do that, you need to have really high temperatures, like lunar noontime temperatures around 380 Kelvin, or when an impactor impacts the moon, it creates these really high temperature environment where water can form and then be basically quenched immediately into the glass that forms, or also be lost to space.
I see. Do we have glasses on the surface of the Earth that have water present in them in a similar way?
We have pyroclastic glasses that do a similar thing. The harder part about the Earth is that it takes a lot longer for things to cool. And so water can diffuse out. Whereas on the moon, because it's a vacuum and it's so cold in the actual space environment, it immediately quenches and is formed into a solid. So it's a little bit more difficult on the surface of the Earth, but there are similar things like the pyroclastic deposits,
but
like
not
quite impact.
My window doesn't have any water in it, presumably.
Right. Right.
Okay. Okay. Thank you, audience, for I apologize for just throwing all of my questions at Casey first, but I was really excited about this, and maybe they were also your questions. But I'm going to start asking the questions that you guys have all been asking.
A lot of good ones in there.
So, did you get? It looks like you did, but someone asked, did you get to fly on Sophia yourself, or did you just say like remotely you should point at that or whatever?
Yeah, I actually got to fly on Sophia twice. It's a very cold airplane and each flight is 10 hours long, and all of my observations occur at the very end of the flight and are usually only 20 minutes long. So I spend 9 hours and 40 minutes sitting on a plane doing nothing, being cold.
Wow. And is that it in your background? Is that Sophia?
Yes, this is Sophia.
Cool.
Oh, it's a lot smaller than I imagined.
I see. So that big gap that allows the telescope to stick out the window or stick out.
It's basically like a big bulkhead door that opens up, and they close it during launch and takeoff. Or takeoff and landing, launch.
Wow, so how many other projects were doing observations, on the flights that yours were on?
So each night they have about, I think it can be anywhere from 5 to 8 different projects observing, depending on how much time each one requires and the objects that are available during a night.
It's cool. is by virtue of it being, the moon and close, is a 20-minute program on the shorter side for a
Yes.
flight, or?
Yes, a lot of programs end up being a couple hours long. The longest you can do during one flight is a 4-hour observing leg.
Okay.
Because you can only fly in one direction for so long before you have to turn around and come back.
Yeah, slow down.
So there's a question: would water of hydration in hygroscopic minerals show up in 6 microns or in IR UV spectra?
Yeah, so if there's any water present, it should be emitting or absorbing at 6 microns.
Okay. Nice. Let's see. Could you tell us more about the asteroid time that was requested on Sophia?
So I'm not an asteroid person, but I am working with a team that is proposing to look at asteroids with Sophia to look for a 6 micron water feature. We are really hopeful that we'll get time, but we find out next month.
Good luck.
Thanks.
Yeah, so you said in comparing the band shapes and such, you were comparing the lunar signal to like asteroid or
those were meteorite samples. So they were measured in the lab. So the water that's on those meteorites is actually terrestrial contamination. But it shows a very similar 6 micron water band as the moon does, which, it kind of makes sense because they're both airless body material.
But presumably, those meteorites landed, or the meteors landed, they turned into meteorites, and then while they're on the surface of the Earth, they slowly like absorb moisture.
Yeah, they absorb water actually pretty quickly as soon as they interact with the surface of the Earth, and especially if they sat there being weathered for a while before they were collected.
Okay. Why is it? I know since the Apollo era, it's basically been, everyone's been like, team moon is bone dry, but we have a bunch of rocks that were brought back by several of the Apollo missions. Why didn't any of those have any of this hydration signature in the rocks?
So that's actually a complicated thing, because as soon as it was returned to Earth, and as soon as you open the capsule, if you're not doing it under vacuum,
it starts absorbing.
Atmospheric water is already on it. So any water that they did detect from Apollo samples was assumed to be terrestrial contamination. They just kind of ruled out any possibility that it was water from the moon. And then in 2008, the Solidol paper, where they measured the pyroclastic glass bead, the volcanic glass bead, they found hydrogen inside the bead, and they saw like a diffusion profile, which is consistent with it diffusing during a volcanic eruption.
I see. Okay. Can Sophia do mid-air refueling to stay up in the air for longer, like 72 hours or anything like that?
I don't believe that would be a thing. That would be nice, but also we have to still observe during the nighttime.
Oh,
so
right.
We'd have to follow
the Terminator.
We'd have to follow sun setting.
Wait, so when it's flying, does it just go out over the Pacific? And because I know it docks at Palmdale. It docks right on the other side of the San Gabriel Mountains from Los Angeles, right?
Yeah. So we so during the flights that I was on, we took off from Palmdale and we flew out over the Pacific. But at some point we came back over the United States, and during the observations that I reported these results from, we were over Nevada on our way back to Palmdale.
Okay, cool. What's the elevation that it gets to that Sophia goes to?
45,000 feet, which is a couple thousand feet above commercial airliners.
I see. Don't want to crash into people, I suppose.
Yeah.
Around trying to take
it. That is true.
Okay, so question, is H2O more useful for a manned presence or a human, a crewed presence on the moon than OH, hydroxyl, or is there not much of a difference in terms of the functionality and the utility?
The biggest difference is extraction of it and then the use of it. So hydroxyl is actually the active ingredient in drain cleaners, and so I really wouldn't want to drink that. But if you want to extract it and then turn it into other things, it takes a lot more energy to break the OH bond than it does to break apart molecular water, so H2O. So when you extract it, it takes more energy for hydroxyl than it does water. And then when you want to break it apart to create oxygen or rocket fuel, it takes even more energy than water would.
I see. Okay, cool. Cool. Well, that was a great presentation. Oh, and it should be noted that Casey has also applied to be an astronaut. Presumably the discovery of water on the sunlit side of the moon will play strongly to her favor should she ever get to go to the moon. So
hopefully.
Yeah. You haven't heard anything yet. I haven't heard anything. Has anybody heard anything? I don't think they've gone to the next step, even though they said they would, but
yeah.
Okay.
How long does the process usually take for previous calls?
So historically, you start with your entire applicant pool, which is like 15,000 people, and they go through a series of 4 cuts, and that usually takes a year and a half to knock it down to like 10 to 12 people. But right now they're trying to make the first cut. The deadline for applications submitted was March, right? I think it was March of this year. They said it was going to be August originally when they got to the first cut, or September, but then they extended it to October because of the pandemic. And I still haven't heard anything, and it's almost December. So not that I would necessarily, but like, I don't know of anyone having heard anything. So,
right.
But I think it's forgivable given the chaotic year of 2020.
That'd be pretty cool. You know, if Casey, you get to go to the moon, Cameron, you just get launched directly into the sun. I feel like that'd be really fun.
I might. Cool. Okay. Well, yeah, no other questions unless you guys have questions for Casey.
Oh, that's great. I learned a lot. I just wanted to know about pyroclastic and water.
We have pyroclastic flows on the Earth too.
Yeah, I didn't know that. I didn't know anything.
Yeah. Cool. Okay. Well, thank you very much, Casey. I hope you stick around, even though I know it's quite late, but do what you can. And then we will have our next speaker, Kishaloy, and I'll let Kaylin introduce Kishaloy.
All right. Well, thank you, Casey, Dr. Honeyball, for that talk. That was really, really great. I'm really excited to introduce our second speaker, the second half. So we have with us, excuse me, Kishaloy Day. So he is a finishing PhD student at Caltech, and for his thesis, he's using wide field optical and infrared telescopes at Palomar Observatory, which is in mountains just south of LA, kind of in between LA and San Diego, I think a little bit on the east line, to search for exploding dead stars in the Milky Way, our own galaxy, and in distant galaxies. He enjoys using new instruments and data analysis techniques for his research. And outside of his research, he loves cooking, binge watching shows, primarily on Netflix, and going on long walks around the Pasadena, I think it's supposed to say Nasadena area. I will also note 2 things. One, Kishaloy is also on the job market. So if any of you audience members happen to have some nice postdoc, lying around, in your fridge or under the, just let us know. Also, many, years ago in the shadow days, Kishaloy and I were on the Caltech Astronomy softball team together, and I can say he was a blue chip athlete with us. And hopefully that wasn't your last at bat. We'll see what the summer holds this year. But today he's joining us, and he's going to tell us about something he's worked on for his thesis work, and it'll be about merging stars. So thank you, Kishaloy. And I will mute and get out of the way, and you can take it away.
Thank you, Kaylin, for that kind introduction. Let's see if I can pull this up. All right, how does that look?
Yeah, it looks good. Thanks.
Perfect. Yeah, right. Thanks, Kaylin. So I'm excited to be talking to you all about some of the research that we do as a group at Caltech, as well as sort of give you a bit of the background about how it used to be done back in the day. So a lot of my talk today is going to be about exploding stars, how we find them, how we used to find them back in the day, and how we find them today, and what these explosions are teaching us about how we got here as a planet in terms of the stuff that we see around us today. So because I'll be talking about explosions, I have to sort of start with telling you about how it used to be done back in the day. So I can tell you that it was really hard work compared to what we do today. So here I'm showing a picture of the famous astronomer Fritz Zwicky using the 18-inch telescope at Palomar Observatory. And like Kaylin said, Palomar Observatory is down in San Diego, in California. In case you haven't had a chance to visit Palomar, I definitely recommend you take the trip once the pandemic is over. It's a beautiful site and with a bunch of different telescopes, and to learn a bit about the history of this observatory and what it has given to astronomy as a whole. So the way it used to work back in the day is that you sit at the telescope the entire night and you keep taking images of the sky again and again. So here I'm showing how you would typically discover a supernova back in the day, which is you take these images on a photographic plate. So here is a photographic plate. You see there are a bunch of galaxies in the center of this image. And you do this again and again, image the same galaxies again and again over different nights. And you look for things that appear in these images that weren't there previously. So here I'm showing an image of this tiny little dot that you can probably squeeze in over here, where you see there's a new star that appeared in this image that wasn't there in an image taken previously. And that's what was subsequently confirmed to be a supernova, or SN as it's called. So as you can imagine, it's a hard job. You have to pretty much stay at the telescope the entire night in the cold weather and take these images again and again. And fortunately, because of the way computers have evolved and the way robotic technology has evolved, we don't have to do this anymore. So that nowadays, the state of the art really is that there are robotic telescopes. So here I'm showing a video of one of my favorite robotic telescopes. This is an actual robotic telescope at Palomar Observatory, which we commissioned a couple of years ago. And what you're seeing here is that there's absolutely no person inside the dome. The telescope is just, it knows what to do. There's a computer that's been programmed to make it decide what to do next. And what it's doing is that it's looking at each part of the sky that you see over here and going there and taking an image of the sky. And all of this data is being recorded on a computer hard drive. It's getting processed with all of the software that we've written. And so that all of this is happening while I'm sleeping at night, so that I can sleep. And also probably I'm just watching Netflix at home. And then just the next morning I have to wake up and look at the data, look at the things that actually appeared in these images instead of sort of doing the eye-by-eye comparison. So at the end of the day, what we're looking for are explosions. And this is a really nice example that I like to show, which is of what these explosions look like. So on the left is an old image of a really well-known nearby galaxy. This is also known as the Pinwheel Galaxy. It's a it has these beautiful spiral lamps, as you can see. And when you take an image of this galaxy in a subsequent night, after this image was taken, you see that there's a star that appeared here in this image that wasn't there in a previous image. And those were historically known as nova stella, or a new star in Latin. And although you might be tempted to say that it's a new star, a star is born, it has a romantic angle to it, but in reality, it's actually not a star being born. It's quite the opposite, which is that it's actually the death of a star. It's a star that was living in that galaxy, but it died in an explosion, and that explosion was spotted by astronomers in this particular galaxy. So in a broad sense, why do we care about these explosions? And this is probably one of my favorite images in astronomy, which essentially shows why we are interested in understanding these explosions in the first place. So here is the periodic table of chemical elements, which some of you may have seen in high school science lessons. And except that it's been colored by what we today understand where these elements were created in the universe. And the one thing that I'll highlight is that pretty much the only things that were created when the universe was born in the Big Bang was hydrogen and helium. Everything else that you see on this table was created inside the core of a star, either while it was living or when it was dying. And in particular, the ones that I'll be talking about are the explosions, which you see are these green and blue boxes that you see here. And pretty much everything that's more heavier than oxygen and all of the common elements that we see around us, oxygen, iron, the iron in our bloods, the calcium in our bones, everything was created inside either an exploding massive star or an exploding white dwarf, the ones that I'll be talking about today. So I think it's a really remarkable plot when you look at it this way. So how do we know that these elements were actually created in these explosions? It turns out that as astronomers, we can use advanced instruments called spectrographs to allow us to map out which elements are present in the explosion that we actually find. So the way we do that is by doing spectroscopy. So here I'm showing what a spectrum typically looks like. So on the top is what white light is. So white light is just a mixture of different colors of elements. So this is exactly what you see in a rainbow. When light passes through a water drop, it disperses it into light of different wavelengths, so that the shortest wavelengths are blue as we see them with our eyes, and the reddest and the longest wavelengths are red. But unlike white light, which is sort of a continuum of different colors that we see, it turns out that individual elements, things like sodium, hydrogen, calcium, these have very distinctive transitions that correspond to very specific wavelengths that you can detect with techniques like spectroscopy. So for example, if I had a source of light where I see that there's a lot of emission corresponding to a wavelength which corresponds to a known transition of calcium or magnesium, then that tells me that whatever is producing the light must have a lot of calcium or magnesium in itself. So that allows us to estimate what is the composition of the stuff that we are finding in the night sky in general. And that's exactly what we do in terms of understanding these explosions, which is that we use some of the biggest telescopes in the world to get spectroscopy of these explosions. So the way it works is that you find a new explosion that was discovered by one of our robotic telescopes that was just doing its thing in the night, and I wake up in the morning and I find one of these new things. And whenever we find these things, we use one of these bigger telescopes to get a spectrum. So here I'm showing two of my favorite telescopes. The left one is again at Palomar, which is a 5-meter telescope at Palomar Observatory. It used to be one of the largest telescopes in the world. And on the right is currently the largest telescope in the world, which is operated by Caltech in combination with a bunch of other universities, which is a 10-meter telescope on the mountain of Mauna Kea in Hawaii. Right, so I'll come back to this plot, and just to lead to what I'll be talking about. So most of the talk that I'll be talking about today are actually exploding white dwarfs and what they tell us about how the universe sort of is where it is today, and the new stuff that we are learning by studying these explosions. The one thing that I'll point out is that just from the start, you see that all of the heavy elements, the metals that we see around us, things like iron and manganese and cobalt, all of this stuff was actually created inside exploding white dwarfs primarily. So in case you are wondering what a white dwarf is, so I just wanted to sort of tell you a bit about what white dwarfs are. So a star like our sun, when it runs out of fuel in its core, so right now it's just burning hydrogen in its core and just converting all of that to helium. But at some point, a star like our sun runs out of hydrogen, and then it expands because it starts burning helium in its shell. And then when it does that, it expands into what we call as a red giant. And essentially what it's doing in that stage is that it's getting rid of all of its outer layers. And once it's done doing that, once it's lost all of its outer mass, what it leaves behind is a white dwarf. And a white dwarf is an extremely hot star. It's a very small star. It's about the size of the Earth, but it has about half the mass of the sun. So it's about half the mass of the sun in the size of the Earth. So it's a very dense region of material. So it has a very high gravity, very high density. And these white dwarfs are pretty common because these are the natural outcomes of what stars like our sun end up at the end of their lives. And the reason they explode is because a lot of white dwarfs that we see in our own galaxy are actually not alone. So like, similar to the sun, which has a bunch of planets around it, there are many, many stars in our own galaxy as well as elsewhere in the universe, which are not born with planets, but they're born with other stars around them. So when you have two stars that are close to each other, they are bound together by their gravity. So they essentially keep going around each other, held together by the gravity. And especially when you have two very close stars, one with a white dwarf and another star around it, the strong gravity of the white dwarf tends to pull material from the star, which is otherwise just doing its thing. And as it's pulling material from the nearby star, it's slowly gathering more and more material on its surface, and it's growing in mass. And as it turns out that as it's gaining more and more mass, starting from whatever the half solar mass that it started from, it turns out that after a certain point, these white dwarfs are not stable anymore. And this is what is known as the Chandrasekhar limit, which is a result that comes from quantum mechanics, where the idea is that at some point, about 1.5 times the mass of the sun, these stars become too massive, they're not stable anymore, so they just collapse onto themselves and produce these remarkable explosions that we can see at extragalactic distances, like the ones that I was mentioning a while ago. So in general, this picture has worked really well in the sense that, for a really long time, for decades, it was sort of almost universally accepted that, these white dwarfs that are accreting material from a nearby companion could actually grow in mass and produce explosions like the ones that we see in distant galaxies, where you get to the Chandrasekhar mass and explode. But as it turns out that, because we are finding more and more supernovae with very large surveys and lots of really good quality data that are available now with bigger telescopes, this picture is turning out to be not quite the right one when we compare it with better data that we have today. And sort of there are various lines of evidence as to why this does not work, but I'd like to talk about one which is sort of most striking, is that, so when you go back to this picture, and when you go back to this picture, you expect that, when you have a companion that was actually transferring all of its material to the star, you'd expect that even after this white dwarf explodes, you'd expect this star to sort of remain behind, so that if you went and looked back at the supernova several years later, you should be able to see that there's a star lying over there that was the culprit in terms of supplying all of the matter to the star. But as it turns out that when you look at these nearby supernovae, so here is the same supernova that I showed earlier on in this beautiful pinwheel galaxy. And when astronomers went and looked at this location with very deep instruments, this is the Hubble Space Telescope, which is by far the deepest the imager that we've ever created. When you look at this location with the Hubble Space Telescope, you see that there's actually nothing over there. So, and this comes as a surprise, because you see that, hey, if there was a big star that was supplying its matter to the white dwarf over there, you should have seen a star that was still left behind, but we don't. So that necessarily says that, clearly this sort of canonical picture where you have a big star supplying matter to a white dwarf that produces the supernova does not quite hold well when you get very high quality data. And the question that naturally arises is, how do you hide this companion that should be there? Because this companion was probably the one that caused the explosion in the first place. So the picture that we are heading to now more and more in terms of the research that we are doing is that the picture that we had initially for these type 1a, for these thermonuclear exploding white dwarfs, this is probably wrong. Instead, what we actually have are actually two white dwarfs that are orbiting each other. So here I'm showing two white dwarfs. So both of these are dead stellar remnants of sun-like stars that instead of having a white dwarf with another normal star, you have a white dwarf with another white dwarf around it. And so what you're seeing here is that these two white dwarfs are slowly spiraling into each other because of gravitational wave radiation. And at some point, when they come too close, they come into contact. They essentially try to merge because gravitational wave radiation is pulling them in. And in this particular case, what I'm showing is a particular scenario that was suggested for a really, really long time, except it was quite the underdog for several decades until very recently. But the idea is that you have a white dwarf that's very rich in helium. So this is the bigger white dwarf that you see over here. This is a helium-rich white dwarf. And this is a carbon-rich white dwarf, the one that our sun will likely turn into, a carbon white dwarf. And as it turns out, there's a very natural way of getting explosions when you have a helium white dwarf that's transferring material onto a carbon white dwarf, like what our sun will turn into. And just to show you sort of a cartoon of what this looks like. So here you have, I'm showing a white dwarf, which is all carbon oxygen, and it's essentially the size of the Earth with half the mass of the sun. So it's very hot and very dense. And when you have material, helium-rich material that's falling onto this white dwarf, what you essentially have is a slowly building helium shell. So think of it like you're just transferring material onto a ball, and it's bound to just keep piling up on the surface of the white dwarf until something happens. And this is exactly what we are now suspect to be the case, which is that at some point, once these white dwarfs start transferring material onto each other, you get an explosion on the surface of the white dwarf, so that you get a helium shell explosion. And this explosion can be powerful enough to sort of blow up the entire star. And this is one of the mechanisms that's really picking up in terms of what we understand these white dwarf explosions to arise from. So, and the natural way how we understand why this is likely the case is because these scenarios have very distinct chemical signatures, similar to the sort of the spectroscopic signatures that I was talking about, in that because there's a lot of helium involved in the system, and because helium burns differently compared to other elements, we can actually use techniques like spectroscopy to figure out how these explosions are produced, and just associate the explosions to these channels. So and the picture that's emerging with these big surveys that we're now able to find thousands of supernovae every year, we can actually study and characterize, get spectra of thousands of supernovae every year. We can now very easily map out which kind of supernova arrives from which type of star, and these big samples are allowing us to figure out the progenitors of all of these supernovae and how they explode and what they produce in their explosions. So just in terms of summary, what have we learned with these big samples that we are able to get now is that unlike sort of the classical picture that used to be very popular back in the 90s, that you have a very massive white dwarf that's close to the Chandrasekhar mass, or 1.5 times the mass of the sun, the thermonuclear explosions, the white dwarf explosions that we see in the universe are likely coming from merging white dwarfs instead of a white dwarf that has a normal star around it. And these are actually pretty common. In the specific the scenario that I was mentioning, which are these helium shell explosions in white dwarfs, these occur about once every 300 years. So I know 300 years might not sound a lot for, but in terms of astronomical scales, 300 years is pretty short. So the fact that we could have one every 300 years is a pretty high frequency of explosions. And finally, in terms of linking it back to all that we see around today, what we can now learn from these explosions is that in addition to iron, which has been sort of the canonical element that we associate with these white dwarf explosions, we can now say that almost half of the calcium in the universe arises from these explosions. And this is something that's really come out of big detailed samples of these supernovae. So with that, I will end over there. Thank you.
Hooray!
Yay, thank you. That was a great talk.
That was great, Kishalay.
I'll even note that in the chat on the YouTube feed, somebody pointed out a postdoc opportunity that you might be interested in. So I think you've got fans in the audience.
Hired on the spot. Right?
Yeah.
From that presentation.
I'll say 2 quick notes before jumping into questions. There's a bunch of good ones from the audience. The periodic table that you showed, that is also one of my favorite, I don't know if you can call it figures or charts, with the extra dimension of information added by the production of these elements. One of the very cool things I remember learning or just thinking about a few years ago. So LIGO, which is jointly run by Caltech and MIT, it discovered these mergers, neutron stars and black holes, eventually led to a Nobel Prize award. The Nobel Prizes, the medals themselves, are made of gold. And one of the things that, not even really maybe the main discovery, but one of the major discoveries was that gold as an element, the discovery process had been somewhat unknown. It had been hypothesized, but never kind of directly, understood. And knowing that, and correct me if I'm wrong, that neutron star mergers or something along those lines produces gold meant that the people who got, Kip Thorne and everybody else who got Nobel Prizes, which were made of gold, got them in part for figuring out, where the gold in the universe comes from, which I just thought was very, very cool. I'll say too, and Kishle, maybe you know this, so you're talking about the historical kind of, origins of how this used to be done. You'd compare these photographic plates and look for new stars. Somebody once told me a story about, I think it was a guy in Australia, this was maybe 10 or 15 years ago, who had a photographic memory and who would look at, I don't know if it was old historical plate data or images just over and over and over to look for new stars. And that for a while, this one person was one of the leading supernova discoveries. Have you heard this, or do you know about this? Or?
Yeah, I've heard of this. I think, before sort of the big surveys became common, the normal people were still the leading discoverers of supernovae. It's still a thing. I think even today, some of the brightest supernovae that we find in the sky are still discovered by just non-professional astronomers, and that's, I think, to me, that's amazing. The fact that that just just out of the regular professional astronomers are still able to sort of discover these things.
Yeah, there's for the audience, there's a supernova. Well, it's really a transient, things that go bump in the night survey, but it's geared towards finding supernovae called Assassin, and it's run out of Ohio State, which is where I did my PhD. And I wasn't involved in the supernova group or the Assassin project, but they search the whole sky or almost the whole sky to look for supernovae, and they focus on very bright events, which was a relatively unexplored regime. And at least, the people who were working on it said that until they came around, Yeah, exactly what you're saying for these very, very bright ones. It was just individual humans. And then even as the survey was coming online, it was still kind of a tight numbers game as to who is discovering more, which, as you say, really, I think speaks to kind of, the impressive stuff that individuals, amateurs and professionals alike can do.
Yeah, I'll add a funny note to that. So the funny part about that is that, before these big surveys came online, the biggest uncertainty for us is, what is happening for around the faintest supernovae, which is, like what can we learn by finding more and more by looking for fainter and fainter things. But now the game has actually turned, because the way astronomy has sort of developed is that we are only looking for the fainter things. Our instruments saturate for bright events, which means that the biggest uncertainty for nearby supernovae now is that what's happening at the bright end, like nobody's looking for them. So there might be a fifth magnitude supernova. Sorry, fifth magnitude is about the faintest that you can see with our human eye, and none of the surveys would pick it up. And so that's become a big uncertainty now for us. So that I think the tables have turned in that sense.
That's so funny. Yeah, it's very interesting. It makes me think of the science that I do, these microlensing searches for exoplanets. It's less true now than it was 10 years ago, but there was a one primary network of amateur astronomers, mostly sprinkled throughout land areas in the southern hemispheres, who would contribute absolutely critical data from their backyard telescopes. Brazil, New Zealand, Australia, South Africa, just all over. And we'd add them as authors on papers. And like one person, I have no idea if she's listening, Jenny McCormick, she's like a single mom who like works a job and just like is interested in astronomy, and also like has made these very important contributions to individual planet discovery.
That's awesome.
Cool. All right, there are a bunch of good questions. Let me see if I can kind of start from the beginning. So Noel Rabina wants to know, how do you make a white dwarf explode? And you kind of touched on it.
Right. Yeah. That's a great question. I think so. I think so. Let me start with sort of the classical picture that was suggested for a long time, which is the idea is that essentially what a white dwarf is a bunch of electrons and protons that are tied together by gravity. And as it turns out that as you add more and more mass to the white dwarf, it gets heavier and heavier. It gets denser and denser. And it turns out that at some point, it gets so dense that the speed of the electrons in that white dwarfs becomes comparable to the speed of light, which means that as you go increasing the temperature of the star, the speed of the electrons has to increase, because the temperature essentially decides how fast the electrons are moving in general. And as soon as you get to that limit where the electrons are moving as fast as the speed of light, the star becomes unstable, because as Einstein told us, in the general theory of relativity, nothing can move faster than the speed of light. So when you start approaching that regime, it becomes that the entire system becomes unstable and sort of implodes on itself. And that's that implosion is essentially what creates a bunch of energy that powers this explosion, and that produces a supernova that like the kinds we see at extragalactic distances.
Yeah, that's a great answer, and it segues really nicely into one of the other questions. This is from Andrew Reitemeyer. So isn't a supernova caused by a white dwarf sucking matter from a companion a standard candle? And he goes on to mention for the rest of the audience as well, that means it has a standard luminosity, which is a tool that we can use. But I'll let Kishaloy take it away.
Yeah, that's a great question. I think these white dwarf explosions have, apart from this sort of understanding what the physics of these explosions, these turn out to be extremely useful tools, even without understanding the physics, because it turns out they have certain relationships. They are standardizable in some way. So in the sense that they have a pretty standard luminosity, in the sense that how bright they get at peak. So that what that means is that if I find a type 1a supernova, regardless of its distance, even if I don't know the distance, if you can tell me how bright it is, I can tell you what the distance to this object is. And that allows us to use it as a tool for estimating distances to very far off galaxies, which otherwise would be very hard to sort of measure, because galaxies can be faint. But these type 1a supernovae, these thermonuclear explosions are the same brightness regardless of which type of galaxy they occur in. So
the same brightness is because the mass of the type 1 of the white dwarf always when the electrons get fast enough to exceed the speed of light, it's always at a characteristic mass, which means that it'll be at a characteristic luminosity when it explodes, correct?
Yeah, I don't know if it makes sense to draw this so linearly, but that fundamental speed limit of the speed of light, you know, arrow helps set a fundamental mass, arrow helps set a fundamental luminosity, and like, you know, allows you to form this relation for standard candles.
Right, but I guess, you know, one of the things that sort of come up with, you know, as I was mentioning, the picture has become more and more complicated with more and more that we are finding now. I think it's really still one of the biggest questions in astronomy today: what causes white dwarfs to explode? Because, you know, like I was saying, if these are not really happening at a fundamental mass, like we are learning more and more these days, then it becomes tricky to explain why they have a standard luminosity, even though we know that they have a standard luminosity. I think It's been tested again and again that, you know, we always find them at a standard luminosity, but honestly, I don't think anyone yet understands why they still explode at a standard luminosity, even if they're not coming from these same mass explosions. That's really the forefront of research today.
And the way that we're able to say that these are occurring at a standard luminosity is because we have an independent measurement of the distance to these galaxies. And so that's how we get this check on that. Yeah, you know, for an exoplanet scientist, I'm going to talk out my butt a little bit, but have people invoked, you know, rotation or some other mechanisms to try to, you know, counteract this or help explain it?
Yeah, that's a great question. I think so. Rotation is, it's definitely, you know, one of the things that's been discussed a lot. The other thing that's been discussed a lot is magnetic fields.
Rotation and magnetic fields.
So it turns out that in the world of astronomy, magnetic fields can solve a lot of problems. Like, you can use magnetic fields to explain a lot of discrepancies. And that was a joke, by the way. But yes, it turns out that there is a lot of work trying to use magnetic fields to explain why this white dwarf exploded at a different luminosity and why this one did not do that. And I think, you know, the rotation and magnetic fields, you know, that's the answer to everything in astronomy.
Yeah, those are the two huge rugs in astronomy that everybody sweeps everything under. Yeah. You know, if somebody asks you at the end of your talk, just like I did, if you considered rotation and magnetic fields, you can tell them, you know, exactly where to go.
Yeah. So so if any of the audience ever finds themselves in an academic astronomical talk, like at a conference or a colloquium, you can sound real smart at the end and just say, well, have you considered magnetic fields or rotation in your models? And then everyone will be like, oh, okay, well, that could explain it also.
Oh yeah. And you know, some of the undergrads will giggle.
They're just hard to model and hard to explain, and they're an extra dial that could essentially produce a lot of the variability that we see in a lot of the results in observations.
Another question, gosh, we're getting a lot of good ones. Is it possible for a white dwarf explosion to generate a gamma ray burst, either short or long, or, you know, are those two phenomena linked in any sort of way?
Yeah, that's a remarkable question, because I think, you know, it's really at the forefront of some of the things that we are beginning to find these days. So, right. So I don't know of just you know, these classical white dwarf explosions to get a gamma ray burst, but one of the things that's been discussed a lot in in recent astronomical research is the fact that when you have a white dwarf that gets very close to a very massive star, say the neutron star or a black hole. So black holes are sort of the remnants of extremely massive stars, you know, not stars like our sun, the stars that are maybe 20 times the mass of the sun end their lives as black holes. So it turns out that there's a lot of work that tries to use a scenario where you have a white dwarf that gets very close to a black hole and it's sort of disrupted because it gets very close. So when you have a low mass object that gets very close to a black hole, it gets, you know, almost tidally stripped apart because the gravitational field is so strong. It's like you know, get pulled out like a spaghetti or something. And then when this white dwarf accretes, you know, sort of transfers this material onto the black hole, you could get scenarios where you have an extremely powerful jet that is produced because of the black hole, and those can produce things that look like gamma ray bursts. And, you know, this is again a lot of speculations for the kinds of stuff that we're beginning to find today. But yeah, I think that's actually turns out to be quite an interesting question today.
Oh, that's cool. I did not know that.
I have a question, Kishloy.
Mm-hmm.
So
Cameron in the back.
In your In your presentation, you were describing how potentially these white dwarfs get close enough together through gravitational wave emission that you start getting mass transfer from one of the white dwarfs onto another. But obviously it has to be much closer than a traditional like massive star companion for it to get within the Roche lobe where it's actually transferring stuff. But what's the time scale for merger when you're already at that proximity to being close enough to start getting transfer? Because obviously the closer you get, the more gravitational waves you emit and the faster it speeds up before you merge. So is there enough time before they actually merge to drop a bunch of stuff from one onto the other where you can like form this supernova?
Yeah, that's, that you just hit on another very big research topic in astronomy today, which is that, so there are two effects here. So like Cameron mentioned, what gravitational wave emission is trying to do is to pull the stars together, so that you'd expect that as it gets closer and closer, it sort of spirals in faster and faster, and you'd immediately merge into something which looks like a supernova or something else. But as it turns out, that exactly at the point where the star starts transferring material onto the white dwarf, there are other effects that's come into play. So there's a lot of angular momentum. So angular momentum is sort of a measure of how fast each of these stars are rotating with respect to each other. And it turns out that when you have these other effects, as soon as the mass starts transferring onto the other white dwarf, you get a lot of other effects that come into play, and what they do is essentially oppose the effects of gravitational wave radiation. So unlike gravitational wave radiation that's trying to pull the system in together, mass transfer actually pulls the system out. And it's actually still a very hot topic of research today, which one wins. We don't know which one wins.
Right.
Yes. So there are two opposing effects that come into play exactly at the time when the mass transfer starts. So, and that potentially could lead to a system where you get enough time to transfer material onto the white dwarf, even before the stars merge. But you could also have scenarios where they just merge directly, and then you could probably get a supernova-like thing anywhere.
I see.
Mm-hmm. That's pretty. This is so cool. So when I was doing my PhD at Ohio State, the Supernovae group, they would talk a lot about this what we referred to as the double degenerate scenario. So this white dwarf plus white dwarf progenitor scenario for these supernova explosions. And I remember, especially as an exoplanet scientist, feeling so cool because like 10 years ago, I won't say how old I am, 10 years ago, it was less well, I would say, like appreciated or understood that maybe that was the more likely mechanism. And I haven't really kind of kept in touch on the field since then. So I'm learning a lot from this. This is great. I'll do one more question. There are several more good ones. Sorry, I'm not getting to everybody's, but thank you for putting it in there. So Larry Harrison has asked if light pollution has affected your spectrographic data in any way, or if that's something that you have to contend with.
Yeah, that's a great question. I think so. It turns out that fortunately, Palomar, most of our observations, the spectroscopic observations, come from the Palomar Observatory, which is sort of in a secluded region in San Diego, which is nice. And essentially what that means is that it's a good place to be at because there's not a lot of light pollution. I think if I remember correctly, when you go to Palomar, before the pandemic hit, you could almost look at the direction in the sky and tell which side is which, because whenever you look out to the Pacific Ocean, it's completely dark. And whenever you look inside, it's like this huge haze of light that's coming from the nearby cities. I think the nearest city to Palomar is Oceanside. So whenever you look in the Oceanside direction, you see this huge haze of light. So I think it definitely affects us. So it depends on which side of the sky you're looking at. Like if you're looking towards the darker sides of the sky, you're probably better off because there's not a light pollution. But it definitely affects us in terms of light pollution when we look at try to look at objects that are towards the cities. Yeah, I think that definitely affects observatories which are closer to LA, the LA area. For example, Mount Wilson. Mount Wilson is so much closer to LA. It's the light pollution is a big problem. But fortunately for Palomar, and even more so for the telescopes in Hawaii, Hawaii is absolutely beautiful when it comes to the conditions over there because there's not a lot of cities around that region. So it's, you're on this mountaintop where there's not a lot of light, and Mauna Kea is still, I think it's the best observing site in the world in terms of the kind of data that we can get.
Well, and in LA as well, the San Gabriel Range, which is effectively the northern border at least at the most populated parts of the county. You know, there's telescopes up there, and
That's Mount Wilson Observatory.
Mount Wilson Observatory, yeah, which was saved from the Bobcat fire. We talked about that a couple months ago, and I just saw a talk on it a week ago. You know, so that this mountain range, which itself provides a good opportunity to put telescopes, it also, you know, has largely kept the light pollution on the north side down, certainly relative to what we see in the southern part of the sky. And so it's nice if you're looking for meteor showers that are in the northern part of the sky, or we're pretty lucky to have a decently good view just a 20-30 minute drive away into the mountains. But, you know, good luck looking at things, you know, more detailed than craters on the moon sometimes on the southern part of the sky. Well, thank you, Kishaloi. Another round of applause for both you and Casey. These are great talks. Good luck to you on the job market. And yeah, it looked it wasn't a job offer in the YouTube chat, but somebody was pointing out a postdoc at a Subaru telescope, which is a telescope that's on Mauna Kea in Hawaii. So yeah, check it out. All right, now we're ready.
Pub trivia.
For the infamous third half of the program. All right. Oh, Cameron, did you freeze? Oh, there you are. Okay. All right, so we're going to do things a little bit differently from how we've done them before. Oh yeah, hi Casey, welcome back.
Welcome back.
So previously we'd used this site called Poll Everywhere, Poll EV. Erase that from your mind. I'm going to use my Men in Black red blinky thing. Now what we're going to do is we're trying a new piece of software that we think is going to be great. So let me go ahead and try to share screen. Let's see if this works. All right, does everybody see that first question?
Yes.
Put up. Okay. So
wait, can you full screen that at all? It's showing your browser.
Ooh, if I full screen it, I can't see. Well, let me move the thing.
I mean, it's okay. It's just, it's smaller than it could be.
No, it's okay. Let's full screen it. All right.
When you mouse over it, it looks like the, oh, maybe when you mouse over it, it looked like the slide itself. It looked like there was the ability to, you got it.
Yeah, does it look full screen now?
Yeah, it looks great. Looks great.
Okay, awesome. So audience members, there's instructions at the top, and these instructions will stay there throughout all of the slides. So if you go to menti.com, menti.com, and you can do this from your phone, you can do this from a browser, any different types of browser, you know, should work, Safari, Chrome, Firefox. Don't you dare try Internet Explorer. We are not here for that. But the other ones.
You can use that if you want. You can use that if you want.
The other ones should work. And then there's a code to enter, 1546279. That might
doesn't need the spaces. You can just enter those numbers directly.
Yeah, you can just put them in. And we'll give people a minute to go ahead and do that. If you want to play along, but for whatever reason you don't want to do the website, you can feel free to put questions in the chat as well, and we'll try to keep an eye on that. So it looks like, do you see people starting to answer? I can see
answers. Looks like people are starting to answer.
All right, so yeah, first question we've got is Arecibo Observatory, located in Puerto Rico, is set to be decommissioned. In what wavelength range did it observe? So we've got microwave, radio, gamma rays, infrared. Let's see, in the chat, we've got radio, high frequency microwave. Somebody wrote LOL. I'm not familiar with that.
LOL.
Electromagnetic spectrum. Microwave. Somebody else wrote my therapy dog. Also don't know about that one. Chris Georgie is asking if it got to millimeter wave. So it looks like there's a lot of, oh yeah, we got some more microwaves, some radio waves. All right, what do you guys think? You guys probably all know Kishaloi, Cameron, Casey.
I do. I have observed on Arecibo. I hope I know what part of the spectrum it operates.
let's see, somebody in the chat said 0.5 to 10 gigahertz-ish. I actually don't know numerically.
Yeah, that's pretty good. That's pretty good.
Pretty close.
Yeah.
So yeah, the answer, drum roll. Oh, cosmic ray.
Cosmic rays. Okay, all right.
It is radio. It is a radio observatory. So Cameron, you've observed there before?
Yeah. When I was doing my PhD, I was involved in a collaboration that did some observations, some 21 centimeter observations so 21 centimeter refers to the wavelength that you're operating at as opposed to the frequency, but it's around, I think that's 2.5 gigahertz. But the idea is you're looking for neutral hydrogen. There's a minor transition that occurs in hydrogen, neutral hydrogen at that particular wavelength and frequency, and it's looking for neutral hydrogen in distant galaxies. So galaxies within redshift of 0.1 or so. And yeah, it was a cool project, and I got to go there for a week and observe. And then from then on, I feel like my advisor was like, "Oh yeah, get to join this, and you get to go to Puerto Rico and observe on Arecibo." And I was like, "Oh, that's awesome!" And I went, and it was really cool. And then for the next 2 years, I observed from my laptop computer in my studio apartment in New York City, as opposed to being able to go to Puerto Rico anymore. And I was like, you tricked me. You made me so I'd work on this project and not be able to go to Puerto Rico anymore. But yeah, it's super sad that it's getting, what's that?
I say I have altered the deal.
It's super sad that it's getting decommissioned. I guess a couple of cables have broken in the last 6 months or so.
Yeah.
I mean, the observatory is quite old. It was built 55 years or so ago, and it's, it's this historical instrument that's been around and done really amazing detections in the radio for a long time. But
and it's been a big cultural touchstone for Puerto Ricans, especially. A couple of my friends are Puerto Rican astronomers, and they're particularly, hit by the fact that this is probably coming down. I did see that there's a petition, going around among some astronomy circles to save it. I don't know if it'll
really
get enough traction, but we'll see.
I mean, all I read was that the assessment was just, there was no way of repairing it and saving it without risking people's safety in doing so, because the cables are so problematic and they risk the entire failure of this enormous dish. So for people who aren't familiar, the Arecibo radio telescope sits in a bowl in like a natural bowl that's formed by a mountain range in Puerto Rico, and it's 300 meters across, isn't it like 3 football fields across or so?
Yeah, I can look this up.
So it's featured in the movies Contact and GoldenEye, James Bond GoldenEye.
Oh yeah, 304.8 meter diameter. 1,000 feet, 0 inches.
Like 3 football fields across, and it's this enormous, what you'd think of as a satellite dish. And then it has the part of the satellite dish that catches all the waves that are focused to it is suspended by these enormous cables, and they're on the brink of failing, and the whole thing could just undergo this catastrophic collapse, and you don't want to be there when it collapses. So they've determined that they should just decommission the whole thing. But it's a bummer because we don't have a lot of instruments in the world like that. There's one instrument that's similar to it in China, in Tibet, called FAST, but it doesn't have all the same capabilities as Arecibo. So,
well, and I'm looking up Green Bank.
I think that's 100 meters.
Yeah, Green Bank is much smaller. It's steerable, whereas Arecibo was locked. It's always facing the zenith. But yeah, GBT is much smaller, and it's great. The Green Bank telescope is great. And similarly, the Green Bank telescope also collapsed in like 1988, and they had to rebuild it. And fortunately, I don't think anyone was harmed during its failure, but it just like fell down one day when they were observing, and it was bad.
Ooh, I didn't know that.
Yeah, that's in West Virginia. Anyway.
Cool. Thank you for sharing. I didn't know that you had observed there. That's cool.
Yeah, it was
Casey
awesome.
or Kishiloy, have you all been down there before?
Unfortunately, no. I wish I had gone to that one though.
Yeah, same. I have also not been there. Kishalo, did you say?
Yeah, I was saying that I haven't been down there, but it's been really fundamental for progress in one of the things that I used to work with, which is pulsars. So, Arecibo, the Arecibo telescope really revolutionized our understanding of pulsars. So, just for in general, so pulsars are these extremely rapidly spinning neutron stars. So, neutron stars are like the white dwarfs that we just discussed about, these the remnants of stars like our sun. More massive stars, things that are about 10 times the mass of the sun, explode and leave behind these things called neutron stars, which are a lot of them can emit radio waves along certain directions, and those can be observed as pulsars using radio telescopes. And the Arecibo telescope has been really fundamental in terms of our understanding of things like how many pulsars there are in the galaxy, what causes pulsars to emit in the first place. So it's been historically a huge instrument in terms of our understanding on that front.
Yeah, definitely. The main thing that I'm concerned about is Arecibo was used to do a lot of things: pulsars, neutral hydrogen detections. It just had an enormous aperture, so it could get a lot of photons, right? But the other thing that it did really, really well was for mapping solar system objects. So essentially what would happen, it was like a radar. It was like radar where it would transmit and broadcast a bunch of signal towards some near Earth object. And the signal would reflect off the surface of that object and then bounce back towards the Earth. And then another location on Earth would essentially get that signal that had been transmitted from Arecibo. So this was done with a variety of different telescopes to collect that. But it was the main transmitter. And to my knowledge, we don't have another facility that's able to transmit the power that Arecibo was. So it may be a really big pill to swallow for the solar system community that uses it to map out the surfaces of different objects in the solar system.
Right.
But something that's notable about that is when you're at Arecibo, you can like run around and you can run underneath the dish, because the dish is suspended off the ground by like maybe 10 meters or 5 meters. So you're running around down there and there are all these lights. And when it's about to transmit, all these lights start flashing and it's like, you can't be down here because you're going to get fried by the enormous amount of radiation that's sent from the transmitter down to the dish and then upward, because some of it will spill through and cook you. And so I ran down there, and fortunately this thing didn't start going, meh, 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 like you're going to die if you stay down here. But that was always like in the back of your mind when you're running around.
A concern, yeah. Let's get on to the next question just before we get too carried away. Let me see, is this full screen? Does that look good?
Yes, looks good.
Right. Question 2, and those of you playing along at home, it should have switched for you. So exploding white dwarfs, that should sound familiar, are known to be the primary producers of which of the following elements? And our 4 options, let's see, what did we set? Oxygen, calcium, hydrogen, and iron. Oh, I just realized we have Dr. Honeyball's initials: calcium, iron, hydrogen. I'm like a really shitty version of Neo. I just see, puns and word jokes everywhere.
It's really remarkable. You're really remarkable, Caleb.
Yeah. All right. Hydrogen, 5%. That's good. That means most people are remembering.
Much like the universe, it only makes up 4% of the universe, right?
Right. Proto-Dr. Day's talk. And think back to the periodic table that we saw a couple times during Kishalo's talk. Iron, oxygen, calcium. Let's see. We've got people saying in the chat, we got some iron, calcium, gotta be calcium. Fe56, Fe is the symbol for iron on the periodic table. We've got some other Fe's, some calcium.
Sorry, I'm getting into my next beer here.
Yeah, Kishalo, what do you think the answer is?
Well, here's a spoiler. There are two correct answers in this choice.
Ah, okay. So we know we can do this reverse. Remembering from your talk, we know it's not hydrogen, because you were mentioning that that we saw in the upper left, I think was a colored dark blue, that was around the beginning of the universe. Okay, so now there's 3 options and one of them is incorrect.
People are doing a pretty good job here. I'm pretty impressed.
Is it iron and, no, sorry. Yes, iron and calcium. Okay, that was close.
Good job, audience.
No, yeah, nice job, folks at home. That was good. I don't know, Keishley, if you have any other. What is your favorite fun fact about calcium that nobody knows that we should know?
Let's see.
The hard questions. Kalen's like hardball here.
Yeah, we got Dr. Honeyball and we got Dr. Hardball.
I guess from an astronomical point of view, it turns out calcium is really common wherever you see in the universe. It's like, and that partly has to do with, a fun fact that it just happens to be the case that the transitions of calcium, like you remember I was talking about the spectroscopic lines that you can see in individual elements. It turns out that calcium is just one of those elements that it's very easy to excite. So, regardless of how much energy you put in, you're going to see it's very easy to excite calcium. So it's just one of those elements that you see everywhere in every star in the universe, in every explosion in the universe. It's just because it's one of those elements that is very easy to excite. And then, when you excite something, you eventually see it cool down and, see the spectroscopic lines.
Oh, that's cool. I don't think I knew that. I'm learning a lot of basic periodic table stuff tonight. This is great. All right, let me go ahead and get it going again. All right, question 3. Good job again, audience, on that one.
Yeah, well done.
Born in Pomona, not so far away, and a graduate of California Polytechnic, I am now the first Black crew member of the International Space Station. Who am I? Kalen Henderson, that is incorrect. That is solidly false. Maybe this one was harder. So he went up with the SpaceX crew. I'm going to maybe get some of these details wrong, but I think it was 4 astronauts 1 week ago, who went up and have docked for an extended stay on the ISS, the International Space Station. Mae Jemison, that is a good answer. We've had a question about her previously. If I remember right, she was the first Black woman astronaut, at least in the US Corps. Victor Glover, he's another astronaut in the US Astronaut Corps. Yeah, maybe this was another Victor Glover. Uh-oh.
Yeah, this is a challenging question.
This is a challenging question. Oh, Victor Glover. Uh-oh. They're becoming sentient.
It's a run-on. James Earl Jones.
James Earl Jones.
Darth Vader, the original Darth Vader. I love it.
Yeah, I answered the questions. Yeah, so I'll say some more facts about this person before giving away the name. So one thing I'll say is that, and I only learned this earlier today, so he, whoever it is, next year could be followed by Jeanette Epps, who would be the first Black woman to be a US astronaut aboard the International Space Station. So we can keep our ears to the ground for that.
With Mae Jemison, she never went to the ISS. She was only
right. She might have been there for. I was reading. There's kind of a distinction within NASA or within the astronaut corps of, are you there for an extended mission aboard the ISS, or are you there doing repairs on Hubble or something, and maybe you dock with the ISS, or maybe maybe you just get it on Airbnb for a night, but you're not doing the 3 months. Yeah, so another let's see. So it is Victor Glover. We'll go ahead and say it looks like people are really loving Victor Glover. He got a bachelor's degree in general engineering from California Polytechnic in 1999. And then in a span of just 2007 to 2010, he earned 3 master's degrees. So one in flight test engineering, another in systems engineering, and another in military operational art and science. I don't even know what that means. I have no idea. But it sounds
operational art. Team 1, go that way. Team 2, take the back. Team 3.
Team 3, do the dance we talked about. Apparently, his nickname is Ike, which is true to NASA form, an acronym for I know everything.
Oh, wow.
That's cool. So yeah, Victor Glover. I couldn't quickly find how long this crew will be up there. But yeah, pretty cool milestone that just happened.
That's awesome.
November 2020. All right.
Hooray, Victor Glover.
Go ahead and share screen again. All right, next question. And good job, audience. Everybody figured it out. We should say, hopefully this goes without saying, knowledge is its own reward. So please do not look up answers before typing them in on the internet.
Google cheating, not allowed, but we can't police it.
Yeah, we can't police it. So the great filter is one proposed solution to what outstanding astronomical question? And so the options are, we've got the existence of planet 9, we've got the origin of gamma ray bursts, we talked a little bit about those tonight, the Fermi paradox, and the source of the far IR, the far infrared radio correlation. And we had a talk, what was it, 3 months ago? By Professor Konstantin Batygin here at Caltech on Planet 9.
Well, and we had a talk by Cecilia Sanders 3 months ago that was about life in the universe, where there was a discussion of the Fermi paradox.
Ooh, the Fermi paradox. Interesting. Let's see, what are people saying in the chat? We've got some Fermi paradox. We've got some Fermi. We've got some Fermi.
Fermi.
Fermi. Fermi paradox. All right. It looks like people are
too far.
yeah. My Freddie Mercury impression is not great.
It looks like Casey has to take off.
Oh, okay.
Thank you for joining us. I realize it's past midnight for you. Much appreciated for your presentation and for sticking around this long. We really appreciate it, Casey.
Yeah, thank you, Casey.
Good luck with your next SOFIA observations, and hopefully we'll see more information about the hydration signature on the moon and perhaps on asteroids as well. So very exciting.
We will see you later.
Thanks, guys. Have a great night.
Thank you.
So over half the audience and most of the people in the chat are saying Fermi paradox, which is the correct answer. So the Fermi paradox, I'll couch it in terms of another kind of formula or question idea that people have in astronomy. So Francis Drake came up with this thing called the Drake equation. And one way of thinking about it is you start addressing the question of, is there intelligent life in the universe or life in the universe? How much of it is there? Where is it? Why haven't we found any yet? And so if you start and you say, we know how many stars are in the Milky Way galaxy. And you start with that number. And then you multiply that by how many galaxies we think they are. So that's, maybe 100 billion times maybe 100 billion. So that's a big number. And then you start saying, well, what fraction of stars have planets? And what fractions of those planets are rocky planets, that could host life as we know it? And then what fraction of those rocky planets around these stars, have atmospheres, et cetera, et cetera, et cetera. Even if a lot of those fractional numbers are pretty small, you usually get a pretty big number at the end. And especially with the genesis of exoplanet science over the past 25 years, we've started to get some handles on the occurrence rate of planets, the occurrence rate of rocky planets. We're starting to look for biosignatures in the atmospheres of of many different types of planets. And so the Fermi paradox kind of takes this and says, well, if you get this big number out at the end of the Drake equation, of how many intelligent civilizations there might be in the Milky Way galaxy, where are they? Why haven't we found them, come into contact with them? Why haven't they come into contact with us? And one of the kind of ways to address this paradox, if we expect that there are so many, why haven't we come into contact with any, is this idea of the great filter. And the great filter is something that maybe it's very easy to get life in the universe, but there's some major bottleneck preventing it from becoming intelligent life, or from becoming intelligent life that can exist for long enough to be spacefaring in a major kind of way. And there's a lot of ideas of what the great filter could be. Maybe it's going from single-celled to multicellular organisms. Maybe it's developing a wall around the nucleus inside your cells. Maybe it's getting some sort of asteroid defense system up before dinosaurs go extinct again, or before the next planetary civilization, intelligent as it may be, goes extinct. One of my favorite fun ones is maybe there is some hyper intelligent species out there for which humans, are just like ants, and they just don't even bother. And they're sitting there waiting for intelligence on a given planet, to reach a certain level. And then they come in and, eat you or destroy you or, colonize you or something like that.
Are you talking about Star Trek?
No, not even. This is a legit idea out there. Like, is the great filter something that we have already passed, and so we're one of the few, or is the great filter something that's in front of us?
I think it's in front of us. If it's out there, it's in front of us, I think.
I agree. I also think it's in front of us. Another one is that, potentially is self-imposed destruction largely inevitable? Is it common for?
I think that's the sad truth.
I think so as well. Whether or not it's climate change or nuclear proliferation, that seems to be a dangerous one too.
Yeah. Two corrections for you. One, you said
okay.
Francis Drake. Sir Francis Drake was an English explorer. It was Frank Drake.
Oh, Frank Drake. No, I knew that. That's funny. I hope Nadia Drake is not listening. His daughter is a science writer. And
oh, really?
Yeah. She writes. Did she write for Nat Geo? I can't remember. You
just shamed her and her whole. Yeah, I mean, maybe Frank Drake is like the great descendant of Sir Francis Drake, the English explorer, perhaps.
Maybe. It's very generous.
The other thing is the Fermi paradox was largely proposed by Fermi prior to the development of the Drake equation, because the Drake equation was like in the late 60s, 70s with Sagan, maybe 80s even. But like Fermi proposed this in like the development of the nuclear weapons in the 40s.
Oh, interesting. So yeah, I guess it's somewhat apocryphal that it came causally.
I mean, it's the same idea, so I'll give you that.
No, that's interesting. Yeah, I don't think I looked at the timeline before. So yeah, I encourage everybody. There's a blog that I really enjoy called Wait But Why. Maybe some of you have heard of it. They have, if you just Google Wait But Why Fermi paradox, there's a really good, and the author of the blog is kind of funny, I think really funny, but deep investigation of the Fermi paradox, and with cute little drawings and this and that. So if you're interested, that's a great place to jump off from. All right, let's get to the next one.
Yeah, let's do the next one. What is the next one?
Yeah, what is the next one? Oh yeah, currently the Leonid meteor shower is occurring. It's a great sentence. What is the next major meteor shower? What is the next major meteor shower? Or the Orionids. That is a good meteor shower. Seen it a couple times. Oh man, maybe some of these questions are harder than I thought.
Well, there's also a lag between when we say it and when it goes to the world.
That's true. That's true.
Plus, we have to give them time to Google the answer.
Yeah.
Ooh, the Cameronids.
I think it's
my favorite meteor shower.
I think it's Cameronids. I don't think it's named after.
Yeah, you're right. You're right. My pronunciation's pretty bad with these sorts of things.
Yeah, no, it's okay. There's no Kalenids or, Kishaloinids. Oh, Geminids.
Okay.
Yeah.
Has anybody in the chat? Did anybody see any of the Leonids that have been happening? I mean, they're still going on. It does extend over like a 2 or 3 week period.
Yeah, and the Leonids has a pretty broad peak.
Yeah.
The one that ends the Trump presidency.
There is unfortunately no astronomical observation that ties to political events that are occurring in this country. But
in the chat, we've got Geminids, Perseids, Orionids. Okay, so there's a bunch of good options. People are, no cheating with Google. Thank you, Dan Cooper. Dan Cooper gets it.
Perseids, okay.
Oh, so somebody said that they maybe looked, but there's heavy cloud cover. Yeah, that's the bane of astronomers, casual and professional. If you think, having cloud cover for a meteor shower is bad luck, I encourage the audience to look up the story of, I think it was a French astronomer named, I'm going to mess up the name, Le Gentil, L-E space Gentil. He, I think, was an astronomer who went through extraordinary lengths to observe, I think it was on 2 different attempts, the transit of Venus. And I will say it did not go well, but I will leave the details of the story, for Google.
That's why we've got Sophia and the Hubble Space Telescope to get above the atmosphere so that you can.
The atmosphere. Oh, we've got the Orion Cameron Gemini shower.
Right.
I haven't heard of that one. The celebratory meteor shower. That's what we should get, January 20th. The Geminoids. I like the Geminoids. Kishaloy, do you know the answer?
I don't. My guess is it's either the Orionids or the Geminids.
Not the Cameronids.
Yeah, not the Orion Cameron shower nids.
Yeah, so it's the Geminids.
The Geminids.
So the Perseids traditionally happen in August. The Leonids happen in November. Those are usually the 2 big ones. And then the Geminids happen in the middle of December. I think they're happening this year between the 9th and the 11th or so.
4th and the 17th. Yeah.
Okay, but the peak is around the 9th to the 11th.
I think 13th, 14th. Looks
Oh,
like.
really?
Sorry, I'm like fact checking in real time.
Right. It is the 13th and 14th.
And the moon.
But this year it's super cool because it's new moon.
Yeah.
So usually what can stymie observations of what would otherwise be bright meteor showers is just the moon is at full phase, and so you have a lot of sky brightness that overwhelms the brightness of the meteors. But the Geminids should be really good this year because it coincides with new moon. So you won't have the moon up in the sky providing all this additional scattered light that's messing up your view of these relatively faint phenomena. I included a colleague of ours runs a private observatory in the Eastern Sierra near Death Valley. And he is having an event there where you can go and observe. Although, I mean, to be honest, you can go to any dark sky site and it will be awesome. Just get away from cities, but he's near Death Valley, so it's super dark. And I'm going to give a talk about stuff there. So there's a link in the thing, but it costs money. So maybe you don't want to go because money costs things.
Yeah, I'll say too. So this is always a little bit tricky with meteor showers. We said the 13th, 14th. That means, when you wake up and it's Sunday, December 13th, stay up that night into the early morning of December 14th. So it's a Sunday night, but pandemic rules, so whatever. And that Monday, the 14th, is our next Astronomy on Tap. It's our last one of the year. So we encourage everybody, go check it out Sunday night, get some rest. We don't start until, later in the evening, and we can all kind of share our observing stories and see what we saw. We could be all watching the same meteors. That would be kind of cool.
And the other thing that's nice about this meteor shower is most meteor showers, some meteor showers, they don't peak until the early morning, like 4 in the morning. And I don't know about you, I don't want to get up at 3 in the morning to go outside and observe this thing at 4 in the morning, because that sucks. But the Geminids peak before midnight. So you can stay up late, go out until midnight, go out until 12:31, set up your deck chair outside and observe these things.
12:31, 12:32, 12:33. There's a lot of options.
Okay.
Wow. Yeah, I tried last year, 2019, the Perseids, which I basically every year go watch. And I 2 nights in a row right around the peak. One night I went early and tried to stay up late. I guess it was 2 nights, one night in between. And then the next time, tried to wake up very early and go. And yeah, it's way worse. It's way worse.
So check out the Geminids. They'll be awesome.
So here's a question for you both. It's a fun question. Don't worry. What is the highest frequency of meteors that you have seen in the meteor shower ever?
So I've seen a good. So my family and I used to go camping in central Kansas at a place called Wilson Lake as an annual trip for the Perseid meteor shower. Usually mid-August. Occasionally timed, with a low illumination fraction on the moon. And I have seen, with naked eye, an honest to goodness ZHR, which refers to zenith hourly rate. So that says if the radiant, the middle of the meteor shower is directly overhead, how many do you see above a certain brightness? Which kind of tells you based on what your light pollution is, how many might you expect to see. I've seen probably about 100, ZHR of 100. So a little bit more frequent than once a minute.
I saw the Leonids in 99 and 2000, and they were like 200 ZHR.
Wow.
Yeah. So you'd see a meteor probably twice a minute, and then saw a couple big fireballs, which was super cool. But for the audience's just reference, there are events called meteor storms, which are incredible. It's like 5 meteors, 2 or 3 or 5 meteors per second, just like. So the Leonids, I believe the Leonids tend to have a 33-year periodicity, or roughly a 33-year periodicity, where once every 33 years you get one of these storms, and you get this ridiculous phenomenon where they're just happening multiple times per second. And it must, to like prehistorical peoples, it must feel like the world is just ending. My God, like just you look up in the sky and everything. But on the other hand,
over, man.
It also gives you a really like innate feeling of how, because all of those meteors are coming from the same radiant, from the same location in the sky. So it must really give you a real good feeling of how the Earth is traversing through space, which is super cool to think about as well. But unfortunately, I don't think there's been a meteor storm like that in modern time. I think there are some paintings that people have done from like 1866, 1833. I don't think anything happened in the 20th century of that magnitude, and certainly nothing has happened in the 21st century. But
and so you didn't see the 1866 one?
No, I'm not that old, unfortunately.
That's too bad. I heard it was a doozy.
But 1999, 2000 was supposed to be the 33-year periodicity when that was supposed to occur, and it happened, but not anywhere near that predicted level. So maybe in the next 15 years, maybe around 2130, we'll see another event like that. But it's challenging to predict the frequency of these things.
Yeah. What about you, Kishaloi? Have you seen a high ZHR?
I think Well, I've never calculated the ZHR. This was the first night I've ever heard of the term ZHR. But I think yeah, I'm not. I was probably 4 years old when the 1999 thing happened, so I haven't seen that either. But I think I was at Palomar for one of these nights when I was just there for work, and this just happened to be one of those nights. And I think I think once every couple minutes is about the highest rate I've ever seen.
I mean, that's pretty good.
Yeah.
No, a ZHR of a couple tens, once every few minutes, like that's a good meteor shower. That's worth the price of admission.
Absolutely.
Cool. Yeah, that's a fun question. Yeah. Gosh, 200 would be wild. That would be really fun. All right, let's get to the next question for everybody's bedtime. All right. Oh yeah, I like this one. Well, I like them all. A review board recently gave a positive affirmation of a joint NASA-ESA venture to conduct a sample return mission from what solar system object? From what solar system object? Okay, Pluto, Saturn, and I'm looking at the chat. Somebody had mentioned that they almost captured a bolide on film.
Oh, cool.
Yeah, that would have been cool.
Bolides are just major meteors. So they're very, very bright. They tend to be fireballs. And a fireball is where you get the track across the sky, but it's so bright that it tends to leave a residual track behind it that continues to glow even after the shooting star passed through. So you look up and you continue to see this kind of glowing line across the sky. Very, very bright bolides will coincide with a noise as that object is large enough that it produces enough sound waves that you can hear the sonic boom all the way to you. So that's what, for instance, in the Chelyabinsk event that happened about, I guess almost like 15 years ago now, in Russia, and it had enough of a sonic boom that it blew out the windows in like thousands of buildings around this location in Western Russia. So yeah.
Yeah. Interesting. So Pluto, Saturn, Europa. Man, JPL has given people a huge amount of confidence in what we're able to get. Oh, we just got a bunch of answers. Mercury, Jupiter, Venus, Saturn, Pluto, Europa. In the chat, we've got some Europa, Mars, Pluto, another Mars. Yeah, so this one we've talked a bunch about sample return over the past 3 or 4 months from a pair of missions, the Japanese Hayabusa 2, and then OSIRIS-REx, the NASA, I can't remember if that one's a joint NASA-ESA or not. This one is actually Mars. So it's a 3-stage thing. Ooh, Enceladus. The first component is the Perseverance rover. So that launched earlier this year. That's on its way. Second is NASA's going to build a sample retrieval lander, and that's going to send an ESA-built rover to get the samples, put them in a NASA Mars ascent vehicle, launch them into Mars orbit. And then the third component is, and this is fully ESA, is an ERO, so an Earth return orbiter that's going to go rendezvous, with the craft that's in Mars orbit, grab that, and then come back and return it to Earth. What I don't know is the timeline for all of that. But this would be the first time that we have brought back samples from, a planetary neighbor. So that would be very exciting.
Oh, someone in the chat brings up the fact that there's going to be a Jupiter-Saturn conjunction in the sky. So Jupiter and Saturn are, from our perspective, they are approaching the same location in the sky. Of course, they're not actually approaching the same location, but the same projected location on the sky. And they will be the closest in proximity to each other in projected space that they've been since the Middle Ages in the next 3 weeks. I think, the next
Ooh,
month.
oh, that's cool. I did not know that.
So,
Thank you, Astro on Tap audience, for keeping
Yeah.
us.
Yeah, good work, Ilondario SL Leon.
Oh yeah.
That sounds very elvish to me.
Never occurred. I'll bet that. Yeah, I don't know. Never occurred in 365 years. That's the same number of days in a year. Illuminati confirmed.
Okay. Let's
All
back.
right, Cameron, I know you poo-poo a lot of things, but you really just need to open your eyes to a new state of mind. Open Your Eyes and New State of Mind, of course, are the two singles off the Yes album, Open Your Eyes.
Oh my God. No, we're not getting back into prog rock. No.
English rock band, yes. It was released in November '97.
No,
and it was after Rick Wakeman, the keyboardist, had left. And who was it? I think it was.
No
Yeah,
more.
Sherwood
No more prog rock. No more Yes. No. I'm putting the veto cane. I'm going to give you the cane and pull you right off stream.
I encourage everybody. So Open Your Eyes was right after Keys to Ascension 2 and before the latter. So go look it up on your own and do some homework.
Don't do it.
It's I don't know if it's worth a listen. 17 is pretty far deep. All right, next question. Oh, hold on. Oh yeah, it was released the same year as Keys to Ascension 2.
Just go to the next question.
A geoscientist recently hypothesized that supernovae explosions may leave an imprint on what surface feature of the Earth? So the options are atmospheric ozone levels, ocean acidity, polar ice cap salination, or tree rings. Atmospheric ozone levels, ocean acidity, polar ice cap salination, or tree rings.
Interesting.
See, looking in the chat.
So when they hypothesized, did they write a paper or did just some dude or lady like, well, I wonder maybe this could do this thing?
No, that it is a published manuscript in a referee
Because
journal.
I can hypothesize all sorts of stuff. I can say like, what would happen if gravity turned off right now? Maybe I'd fly into the atmosphere, you know.
Yeah, it was the International Journal of Astrobiology. So maybe this is going to help. And it was published by a researcher, I believe, at the University of Colorado at Boulder.
Now you're giving all these spoilers. These Google audience members are just like.
I think there's no way we can lose, in our universal garden. From the balcony, I hope that somehow, someday.
Are you quoting prog rock? Are you quoting Yes?
All right, so we've got a lot of love for tree rings. We've got nobody likes ocean acidity, polar ice cap salination.
It seems interesting, right? Because so a supernova goes off, it injects a bunch of ionizing radiation into the atmosphere. I guess you could have that, let's see, that could presumably affect atmospheric ozone levels.
Yeah, so writing the false answers to this was actually really tricky because, the researcher didn't necessarily hypothesize all of these things, but I wasn't necessarily convinced.
But you did. You falsely hypothesized these things.
Intentionally and falsely, I did.
Polar ice cap salination. I don't know about that one. I mean,
that one was
and then there's a little bit of salt left over.
Yeah.
Ocean acidity, maybe.
So
Tree rings seems kind of crazy though. Like, is it really gonna affect the overall luminance of the year, or I don't know.
Yeah, I don't know about that one. So in the chat, we've got some tree rings, ozone, C14 and tree rings. That refers to a specific radioactive isotope of carbon, C14. Somebody wrote magnetic fields. Yeah, that, rotation.
And rotation.
Tree rings. Cosmic rays mess up the ozone. Ozone would have recovered by now. So the answer, do you guys know? I would not have known this, I don't think, if I hadn't.
I know because you showed me the answer, but I wouldn't know otherwise.
I wouldn't have known. Keisha Lloyd,
That's
do
a
you know
hard-
this?
Oh boy.
Question.
Okay, this is a hard position. Let's see. If I had to guess, I don't know the answer, but honestly, if I had to guess, I'd say it's the polar salinity thing.
Interesting. So it's tree rings. It's tree
It
rings.
is
That
okay.
surprises the hell out of me.
Yeah. So the story goes, so you can look at you can basically carbon date the tree rings, which I didn't know. And so you can look for the person in the chat who mentioned this had it spot on. So you're looking for the hypothesis, at least, is that you're looking for higher levels than you would expect from a normal annual cycle of C14 of this radioactive carbon. We know the half-life.
Oh, so it's the ejecta from the supernova producing additional it's not any kind of luminance or radiation. It's
Right.
actual ejecta.
That right? Which to me seems, I don't know. I like it.
Yeah, I would not have guessed that.
I would not have guessed that. It seems like a pretty minimal effect, but
But yeah, I encourage everybody, this is Astro on Tap. You can go look up the paper, UC Boulder, tree rings, sciencedaily.com.
we'll include the link in the description when Kaylin is
Oh
done.
yeah, I'll send this around. All right. Next question.
Send me the paper and I'll put it in the description.
Yeah, I'll chat it here in a sec. All right, next question. We've got, oh yeah, it's too bad Casey left. Why had no one used 6-micron spectroscopy to look for a molecular water signature on the moon before now? Why had nobody done that? All right, Cameron, I'm gonna chat you.
You're gonna chat me. Uh-oh.
Yeah, so I'm giving Cameron the link to the tree ring article. So then everybody can go read, see what they think about it. So why had no one used 6-micron spectroscopy to look for molecular water signature on the moon before now? So we've got hatred for 6 microns. Too busy looking at Mars.
So you can see the effects of the alcohol kicking in now.
Idiots. Ooh.
Oh, I like this audience is spicy.
Yeah, everybody's feeling. In the chat, we've got lack of imagination. Another one, unable to do so without equipment. So maybe they didn't have the right equipment. In the chat, Earth's atmosphere has too much water.
True.
And we have no space-based instruments at that wavelength that can image the moon. Because the moon was thought to be dry, that's potentially related to the lack of imagination.
Yeah.
Yeah.
Idiots. I really like
Fools. Another person in the chat says no instruments to measure it. So yeah, that's a popular hypothesis. It's a good idea.
Yeah. So in the absence of Casey, since I'm not actually Casey, and I've done some lunar hydrology public like science before, but I think the answer is a collaboration of many of these things.
Yeah, I think the audience, you got it pretty right on.
Yeah. 6 isn't as cool a number as 3. That may be the most.
I mean, three is a prime number.
Yeah, that's true. 6, no way.
6 is, 6 too even. It's not odd
Yeah,
enough.
But I think the main thing was there weren't a lot of instruments for being able to pick this up. The original 3-micron signal was picked up by a couple of different things, by Chandrayaan, the Indian mission that passed over the moon, and there was another mission that picked it up. It wasn't as easy to get to 6 microns, and then honestly, I think there was the general assertion that the tradition was that everyone thought the moon was dry. Ever since Apollo, everyone thought the moon was dry. And so the presumption was that the signal that people were picking up with these more modern day observations was hydroxyl as opposed to water. And so there wasn't really a big push for it. So, kudos to Casey and Casey's collaborators. I mean, Casey was the PI. Like the news reports that you read over the last 3 weeks saying there's water on the sunlit side of the moon, that was Casey. She was the first author on those papers. Like big shout out to Casey. She rocks and rocked the house with that. So, but honestly, I just think it was a lack of a lot of instruments to be able to do that, but then a lack of people's motivation to go and find an instrument like Sophia. We can apply across the US and apply for this time on this national infrastructure to be able to observe this. And she did it and she found it, and that's awesome. So, basically all the responses that we got between like 6 isn't as cool as 3, or lack of equipment, or idiots, or no one thought of this before.
Imagination.
So maybe not idiots. Let's not call all lunar planetary scientists idiots. I wouldn't. But
this actually brings me to sort of a general point, which I think is true for astronomers in general, which is, and this just might be me drunk talking, all kinds of,
Hit it.
Yes.
I'm on my board. No, let's keep rolling.
But in general, I think it's true that the universe is much more creative than what human imagination can do. So I think whenever astronomers go into exploring a new phase space, there are bound to be discoveries. Like you will find stuff that you never had expected before.
Mm-hmm.
And that's just because, I think nature is much more creative than what human imagination has the capabilities of doing. So that's just me talking drunk, but I think that's true.
Oh yeah, you're 100% right.
Exactly correct. I think you're right. Whenever we open things up, we find things that we never could have predicted because we're too set in our like mindset that's either been dictated by tradition or preconceived notions or what have you. And then you're like, oh, fast radio bursts, what the hell are those? Or
it makes me think of there's the metaphor that's maybe particularly apt for an Astro on Tap night of you're drunk and you're walking home and you're trying to find the key to get back in your house or your apartment, and it's nighttime. Where do you look? You look under where the lampposts are because that's where you can see. Well, as astronomers, it's our job to build a lot more lampposts so that we can we don't want to ruin the night sky, but so that we can look a lot more places and think about where we actually want to push and find new discoveries, as you're saying. So yeah, I totally agree.
That's a good analogy, and I'm really glad you didn't start quoting a prog rock band when you. That was really what I was worried about.
I saw like a flicker across your face, and I was like, "There's still time."
Oh no.
Yeah. There's still time and a word. That's another album by Yes.
Stop.
All right, let's get to question 9, the ultimate question. All right, when 2 neutron stars collide, it is thought that they form either a black hole or what other type of astrophysical object. So the options we've got here are a magnetar, a charm star, a red supergiant, or a white dwarf. So when 2 neutron stars collide, what is it? Black hole or an astrophysical object? All right, we got some love for charm star.
Oh, yeah, charm star. See
what we got in the chat. Give it a second.
The most charming option in those 4.
Sure, you get it. Magnetar, charm star. Okay. In the chat, we've got some magnetar. Oh, we've got some white dwarf. Okay. Some more magnetar in the chat.
Oh, it's going full magnetar here.
Yeah, full on. Maybe quark star from the chat.
Okay, okay.
We're throwing out some ideas. I like it. I like it. Yeah, somebody said, I think you want magnetar, but why not a quark star?
Why not?
Yeah, riddle me this, astronomers. Astronomy nerds. Magnetar is just a cool word. I totally agree. I remember the first time I heard it in probably a colloquium my first or second year of grad school, I was like, well, that person's drunk. That's definitely not a thing. It turns out I was incorrect, and it's definitely a thing. Never go full magnetar. Yeah, you never know. You never know what happens. What is the limit between neutron star and black hole? 3 solar masses? Kishloy, do you know that number off the top of your head?
I think 3 is the number that a lot of astronomers accept, but it's
yeah.
Yes.
Yeah, I think because it's about 1.4 solar masses is the threshold between a white dwarf neutron star, or thought to be. Is that around the progenitor?
Yeah, I mean, I guess 1.4 is sort of the most massive a white dwarf can get. So,
right. Yeah.
Neutron star is typically sort of 1.5. That's the number. But the most massive neutron stars we know of are like 2.5 solar masses. So we don't know of anything more massive than 3 solar masses that's a neutron star.
And it looks like people are converging. So Kishloy, is it okay if I let you field this one? I feel like this is in your wheelhouse, maybe more than mine.
Okay, yeah, sure. Right. So I think, if I understand this correctly, I think the magnetars would be.
Yeah, correct.
Yes. Yeah. Mm-hmm.
Yeah. Can you tell a little bit about magnetars?
Yes. Yeah, right. So magnetars are pretty exotic objects in my opinion, which is magnetars are essentially neutron stars. So neutron stars are again the kinds of dead stellar remnants that are left behind after the stars that are more than 10 times the mass of the sun die in these explosions. And magnetar is a special kind of neutron star in the sense they have very strong magnetic fields. So the name really magnetars comes from the fact that they have very strong magnetic fields. It's not I think it's creative, but it's a very catchy name in my opinion. Yes. I think one of the leading suggestions about what might happen to merging neutron stars is the fact that instead of sort of directly collapsing to a black hole, you might get a magnetar, which is extremely magnetized. It's very massive because you have 2 neutron stars that are merging into each other. So they have a lot of mass in that merger. And magnetars have been sort of one of the leading suggestions regarding what might happen to these merging neutron stars.
Is there an easy way to understand, maybe astronomers don't know, what the kind of main factors are that determine if you are 2 neutron stars and you merge and you form a magnetar, or you go a different pathway?
Yeah, I think you alluded to the answer already, which is astronomers do not know.
Have they considered rotation?
Right, but I guess, let's see. It depends a lot on the very uncertain physics of sort of what happens, because these neutron star mergers are probably one of the most enigmatic environments we see anywhere in the universe, and there's a lot of sort of uncertain physics over there. Things like what does material behave like at very high densities? We don't know the answers to those questions, and I think we're still trying to learn about what happens to them based on sort of getting more and more data on these objects. But I think at the end of the day, it eventually boils down to sort of understanding how much matter is expelled in the merger as opposed to sort of that remains bound to the merger, because you'd expect that the more the amount of mass that is still bound to the merger, the more likely it is that it's to collapse to a black hole, because it's just way too massive to stay as a neutron star.
There was an interesting callback in the chat. didn't Chris present this before? I think the this is referring to neutron stars or pulsars, and probably Chris Bochenek, who we heard from. Was that last month? 2 months ago?
It was last month.
Time has no meaning in 2020, but yeah, that's a good callback to a previous AM Tap Talk. Cameron, would you like to tell us a little bit about charm stars?
Charm stars are something that I made up this afternoon. So they're potentially related to quark stars, given that there are charm quarks, but it seemed like a feasible enough idea, given that there's the idea of quark stars and the idea of certain quarks prevailing and forming some sort of stable object. So I just made up for charm stars.
Oh, man.
And just to confirm that, I looked up charm stars and it shows a bunch of like charm bracelets with stars. Yes, it's totally BS. It's totally fiction. So
yeah, so Astro on Tap LA audience, you heard it here first.
charm stars. Almost as ridiculous as prog rock.
I was gonna say Quarks Prevailing would be an epic album title. Like, let's be honest, that would be right up at the prog rock wheelhouse. All right, last question. Longtime fans of the program know that we always have a question about the documentaries of the Star Wars. So a once lush and verdant planet, now a volcanic hellscape, what planet served host to the lightsaber duel between Obi-Wan and Anakin? What planet served host to the lightsaber duel between Obi-Wan and Anakin? Oh man, I was reading in the chat and somebody mentioned the weak force and the strong force, and I thought they were talking about Star Wars. No, previous question. Oh, that's a great segue. We got some Jakku, Tatooine, Jeddah, Mustafar. Somebody said Kepler 10b in the chat. That's great.
Tell me about Kepler 10b, Kaylin.
Kepler 10b. Yeah, let me check the internet. That's when I should.
Oh, I thought that was your jam. I thought you were living on.
I'm more of a Kepler 10c kind of guy.
Okay.
Oh yeah, this was the first rocky planet. So, and this one, it had a pretty short orbital period, so it was thought to be, scorched Earth. Anyone ever played that game?
Oh yeah, classic.
Classic, the mother of all games.
Yeah. Well, I wouldn't go that far.
No, that was its own subtitle.
Oh, was it? Really?
Yeah. Somebody else said Earth.
Ooh, we've got Where the High Ground Is.
Which is where the higher ground.
Yeah, poignant line in the film in episode.
Yeah, from my perspective, the prog rock isn't evil.
No more. Yes. No more
someone said Earth. Someone else said Mustafar. Someone said what Star Wars?
Evidently, what Star Wars is the leading response in our word.
So I think I was noticing this throughout our word cloud answers. I think it's the most recent one.
Oh.
That's my hypothesis.
Well, somebody has to respond again, I guess.
Yeah. Keisha Lloyd, do you know the answer? How familiar are you with the documentaries of the Star Wars?
I am not very familiar. I do not know the answer to this question.
Do you think the audience has said the answer or not? Well, maybe it's not the most recent. Looks like, okay, maybe I was wrong on that.
I trust that the audience is more aware than I am.
That's fair. They know a lot about magnetic fields, charm stars, and Star Wars.
Well, I haven't yet watched any of the new Mandalorian season, so I'll have to integrate some of the new planets from that. But
well, and I think this planet was featured, so it's definitely in episode 3, which was when this lightsaber duel took place.
Yeah, that's right.
Was it shown in any of the new trilogy or Rogue One?
Not to my knowledge. It might have been in Solo, but I don't think so. I think it only showed up in episode 3. Let me do some searching here.
Yeah, we can do some. We're gonna get back to you and do a. Oh, yeah, it said it did appear in episode 9 and Rogue One. I do not remember it.
I don't remember it in episode 9.
I definitely do not remember it. I don't
And
remember
in
it.
Rogue One? No, it wasn't in Rogue One. That's outrageous.
This is the second sentence of I'm not even on Wikipedia. I'm on Wikipedia.
Well, Wikipedia has been known to be wrong.
Never.
It is edited by jokers like you and me. You're sitting there as a Wikipedia editor adding in all kinds of prog rock references into things that
they've got me covered on that one. They've got me covered. It is. Right. The answer is. Do you want to say?
Mustafar.
It's Mustafar.
The volcanic scape, where the epic battle between Anakin and Obi-Wan takes place. Probably the least bad scene of the entire prequel trilogy, I would argue. But
I thought the scene in which movie was it where there was like a big arena and there were like 3 creatures.
Oh, that was just an abomination. That was the end of episode 2. That was so bad. And then Mace Windu pulls out his purple lightsaber and he's flinging it around.
I remember reading an interview with Samuel L. Jackson, and it was about the origin of the purple lightsaber. And he wanted a purple lightsaber because no one else had a purple lightsaber. And the reason being that in like the distant shots of the battles, he wanted to be able to point out which person was him. And that's the origin of the purple lightsaber.
That's fair. That's what I do.
It's,
but I am in fact not a Jedi in the Star Wars universe, so or an actor portraying one of them. Anyway, all right. Well, congratulations to our peoples who nailed this quiz. Good work, team. We had some good questions. We had some maybe not so great questions, and we had some prog rock references, which were definitely below the tier. So
excellent. Thank you to Kishiloy and to Casey, who's not here, but thanks to both of you for giving talks. Great work.
Absolutely. Thank you guys for your presentations. They were excellent. And we wish you luck on the job market, Kishiloy. The job market sucks, especially during COVID, as I'm learning right now. So, but I'm sure you'll get a good job. I have no doubts. All right, so other things to advertise. Yeah, check out the descriptions in the links in our description for Spanish language astronomy public lecture events that will be coming up soon on a YouTube channel that we've linked. Check out other Astronomy on Tap events and their YouTube live broadcasts and recordings. Check out the Geminids if you have the opportunity. The next meteor shower that's going to take place in about 3 weeks or so. It'll be at new moon. Get to a dark sky, get to the darkest sky that you have the opportunity to go to. The link that we have in the description is in Death Valley, so it should be pretty dark. But honestly, even getting away from a major city, you should, just set up a lawn chair, bundle up in a blanket, and just look up in the sky towards Gemini if you can. And before midnight, you should see some pretty good meteors and potentially some fireballs. Hopefully not any fireballs that like blow out the windows around you. That wouldn't be good. But
that would be cool.
Could also be super.
Yeah, and that is Sunday night, December 13th. So just stay up a little bit late that night and then sleep in on that Monday the 14th. And then that night is our next Astronomy on Tap, last one of the year. And we'll check in and see what we saw.
And come back. And we'll all talk about
the same
meteor showers and Geminis. It's going to be awesome. So do what you can. And I misspoke. Our next stargazing public lecture is not December 18th. I think it's December 4th, which is a week from this Friday. and it's going to be awesome because Vikram Ravi knows his business with radio astronomy. So thanks for coming, everyone. We'll be back next month. Have
Stay
a good
safe.
evening.
Wear your masks.
Wear your masks. The pandemic will be over soon. Vaccines are on their way.